But this week is primarily intended to discuss about the complexity. So before going to the complexity, we want to look at some other things. So first of all, what are algorithms, right? So when you have a problem to solve, you come up with a sequence of steps and you say that, okay, I have a certain problem to solve. And for this, I get a certain input, which might be given by the user or which may not be given by the user. But I have a certain input that goes into this algorithm, which is subjected to the sequence of steps. And there is a set of output that comes out of it. Okay. So I'll just share the screen so I can write something. Is the screen coming?
Yes, ma'am.
Excuse me, ma'am.
Yes, ma'am.
Yeah.
Ma'am, the YouTube links will not be available on calendar.
No, it will be available for this session alone. There is some technical issue from our side. We were not able to get the YouTube link. So for now, we are recording it and we will upload it on YouTube.
Okay, and ma'am, it is there. I think it will be uploaded in the this section also where we have all our lectures.
Yeah, there is a YouTube live sessions link, right? There you will get that YouTube ID, just like the other live sessions.
And ma'am, on the for further weeks also, do we get these live sessions on calendar? These YouTube links for for this live
Yeah,
sessions?
yeah.
Okay. Thank you, ma'am.
Yeah. Okay. So you can say an algorithm is something like this, right? This is an algorithm. You have an input and you have a certain output. Right? So now what you want to do is you have come up with a sequence of steps, right? And you claim that your algorithm works, or rather it works correctly. In other words, for every input that you give to this algorithm, it produces the correct output. So what do you mean by the correct output? Say, for instance, you want to sort a list of numbers. The output is the sorted list. And if it is in ascending order, it should be in ascending order. If it is in descending order, it's in descending order. So you get these test cases when you are writing the program, right? Even on the portal or even on for OPP or whatever, you get the test cases. So suppose you pass something like 4 test cases out of 6, or say 2 test cases out of 6. There is a high possibility that your whole program logic, which in turn is what the algorithm is all about, in itself is wrong. Right? So the test cases are not passing definitely means there is some issue with the program. It could be some Python related issues which you probably are not aware, but it is also possible that the logic of the program was wrong. But suppose all the 6 test cases pass. Can you claim that your algorithm is correct? Can you claim that for every input your algorithm works? What if I give a 7th test case and it fails? And this scenario can happen even if you give, say, 1 lakh test cases, your algorithm or your program could fail for the 1,01,000th input. And hence, to claim or to prove that your algorithm is correct, it is always important to have correctness proofs. This is the first and foremost thing about any algorithm study. You write an algorithm, you have to mathematically prove. So this is using some mathematical steps, mathematical logical steps, right? There is a mathematical proof that has to be there to show that your algorithm works fine. So in this course, we are not focusing very much on the proof. We are not focusing on the proof at all because it's more like a subjective thing, right? But as an algorithm student, you should be aware that the first and foremost thing in coming up with any algorithm is to prove its correctness. And there are many techniques to do that. So sir is actually discussing about something called loop invariant, right? So that is one technique. So you have to find a loop invariant. So I'm not discussing those in detail here. This is loop invariant. Then there is some technique called proof by induction. Then there is another technique called proof by contradiction, right? So these are all just for your information, but these are very important as an algorithm student. You are expected to appreciate the importance of correctness proofs. Okay, that's the first thing about algorithms. The second thing is, okay, I have got an algorithm and I have written a proof for that. Now, what is the feasibility of using this algorithm in a way that will give me a result in a reasonable amount of time? Can we be assured that I can get an output of this algorithm in a reasonable amount of time and using a reasonable amount of memory space? So this is where the complexity of algorithms, the study of complexity of algorithms comes into picture. Okay. So suppose you are traveling from, say, Chennai to Bangalore, and you are stuck somewhere in the middle and you're accessing the Google map. And if it's going to, try out all possible paths from Chennai to Bangalore, it will probably never give you a result in years. It could be what is known as an exponentially hard problem. But you still have to get the a feasible route in a reasonable amount of time. So this is where the analysis of algorithms, the study of the complexity of algorithms become important. So the complexity of algorithms we study from two perspectives. One is with respect to the time that the algorithm consumes and with respect to the space. So in this course, again, a lot of our focus is limited to this part, which is the time taken by the algorithm. So then again, okay, there is then one more thing which we are not going into at all. This is like advanced algorithms, but once you have a solution which is kind of feasible, can you improve the performance? Can you come up with an algorithm which is kind of optimal, which has kind of an optimal performance? And are you able to show that you cannot do any better than this? Any better than the algorithm that I've come up with? This is the most optimal kind of algorithm that anybody can come up with. So this is something like optimizing or something like improving the performance of the algorithm, right? So that is a different part of it. So you have something called exponential algorithm, then you have polynomial time algorithm, then you have linear. I will come to all those, but just telling you like, so you can actually improve from one to the other by using some very clever techniques. So this you can totally ignore for now. This part is something more advanced. So in this course, we focus on the time part, the amount of time that is used by the algorithm. Okay, so far good. Is it okay?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Yeah. So now we have, how do you measure the time? Right? How do you measure the time of the algorithm? Say, suppose I have, or rather, how do you say that one algorithm is better than the other? Suppose, say, algorithm 1 has 1,000 lines of code and algorithm 2 has 100 lines of code, which both achieve the same result in the sense that both are proven correct and all that. Does it mean that algorithm 2 is any better than algorithm 1? It need not be, because the 1,000 lines do not really imply the running time, right? It probably implies that, it is more written better, or, it is more readable or whatever. But eventually, it does not imply that algorithm 2 is any better than algorithm 1. So how do we look at the time complexity? In order to look at the time complexity, we look at a certain parameter which keeps changing. Which actually gives us an idea about what happens when there is a large input which is given to this algorithm. See, for the smaller input, say 5, if there is a list of say size 5 or 6 or 7 or 8, almost all algorithms would possibly behave the same. But when it crosses say 10,000, say 1 lakh, that's when the real difference starts to come, right? So how do we define, what parameter do we want to define to understand the complexity? For this, the parameter that we use is the size of the input, right? So size of the input is again something that you have to understand. Depending on the problem, we define what is the size of the input. Say for instance, in the case of sorting algorithms, right? You have say sorting algorithms or the searching algorithms and all that, right? So here, the number of items in the list that you want to sort. This is the size of the input. So if you want to sort a list of say size 10, and if you want to sort a list of size say 1 lakh, it will have a different performance. The one with the input with 1 lakh records will take much more time than that with the 10 records or so, right? So the number of elements in the list or the number of items in the list is a size of the input. In the case of say you want to find the GCD of two numbers, right? Or in the case when if you want to find out say if a given number is a prime number, or you want to find out say the number of ones in the binary representation of a number. For all these things, you cannot say that the number of items which is given as input is the input size. Because in the case of GCD, you're always giving two values. In the case of is prime, you're giving just one value all the time. In the case of number of ones in the binary representation of a given number, there is only one number which is the input. So here, if you take the number of elements in the input as the size of the input, to identify a parameter which will keep changing and which will help us come up with how the algorithm behaves asymptotically. So asymptotically means as the input size approaches something like infinity, right? So when it is approaching a higher value, how the algorithm behaves, the asymptotic behavior of the algorithm. This is what we want to figure out. So for this, we are going to use the input size as the parameter. And this depends again on the problem that we are going to use. Because in the case of sorting a list, searching for a list, etc., the number of elements in the list is what matters. In the case of finding the GCD, is prime, number of missing, etc., what matters is the value or the number of, say, if you want to find the number of ones in the binary representation of 32, and if you want to find ones in the binary representation of, say, 2048, right? So these both are like totally different. I mean, this 2048 is definitely going to take more time. So the value or the size of the input here is the size as such, the value of the number that you're inputting, right? I mean, number of iterations that are required to find a solution will depend on the size of the value of the input. Say, for instance, you want to multiply two matrices.
Ma'am, can you repeat that binary part?
Sorry?
Can you repeat that binary
Sorry?
part? Binary part you told. Something like binary.
Yeah. So one second. Yeah. This part, number of ones. This one?
Yes, ma'am.
Is this your question? Yeah. Okay. So if you have, say, 32, right? You find the binary representation of 32, which is 1, 0, 0, 0. Do you know what is a binary representation of 32?
8
What is it? 8 ones, sir.
Is it base 2? 5 ones, man. 5 ones.
This is 32, right? This is the binary representation of 32. Right? Okay, that's okay. I mean, you don't have to worry about it. But what I'm saying is, you have to figure out this number, right? To get this number, every time you have to do this. So you divide by 32, again divide by 2, again divide by 2, again divide by, so however many, so here the remainder is 0, here is 0, here is 0. So that's how you get this value, right? So finally, it depends on the size. So if it is 2048, you have to divide it by 2 so many times, right? Right? You have to divide it so many times, right? So the value of this number is what will decide the number of iterations that you need. Got it, no? There may be efficient algorithm. I'm talking about probably a naive algorithm. There may be shortcuts in which you can find a binary representation by simple hardware. There may be hard-coded firmware software which you can directly compute the binary representation. All that. Leave all these things apart. I'm talking about a general, simple, straightforward algorithm where you keep dividing this by 2, and when you get the final binary representation, you simply count the number of ones in that. So here you cannot say that the input size is the number of inputs. It's the value of the input that will decide the number of iterations. Is this clear?
Okay, ma'am. Yes, thank you.
Okay, so you have, yeah. So the other example what I just wrote is if you want to multiply two matrices, right? Then the number of rows and columns is the input. That's the size of the input, right? That is what is going to decide the number of iterations and hence the complexity. Because you have to multiply the first row of first matrix into the first element of the first row of the first matrix into the first element of first column of the matrix plus the second element of the second element of the first row of the matrix. You're getting the point, right? So depending on the number of columns and number of rows in those matrices, the complexity of the algorithm changes. So deciding on what is the input size for an algorithm is an important factor in deciding the time complexity or in analyzing the time complexity of an algorithm. Okay. So this will come with practice, but even say, for instance, I can tell you another example. You have a set of numbers, say a set of n numbers, and you want to find a subset of size say k, which has the highest sum. So suppose you say you are giving input as say n equal to 10 and k equal to say 2. It might be an easier computation, or maybe the one with the bigger set might be an easier computation, whichever way. But then the input size is now n and k. So your time complexity will depend on both of these. So you have a big list and you want to come up with a subset of size k, which has the highest sum. So this is another kind of an input where the size of the input is different, right? You understand what I'm trying to say, right? Is this clear? The last example, what I explained to you?
Hello,
So
ma'am.
for instance, say you have, say,
Yes, ma'am.
Yes, ma'am.
Can you
yeah,
say
somebody is
once
asking
more?
something. Yeah. This one, right? Yeah, I'll tell you.
Yes.
Okay, say for instance, 1, 4, 6, 8, 5, 3. Okay, so here you have a list of size 6. So n equal to 6 in this case, right? Now I'm saying k equal to 2. I want to find the subset with the maximum sum. So this is one pair, this is one pair, this is another pair, right? This is another pair, this is another pair, etc. So you get so many pairs here, right? 1, 4, 4, 6, then 1, 6, etc. You get so many pairs and you want to find the maximum largest sum, right? In this case, suppose your k is say 5. Then you can take this one and this one, right? And then the number of sets is like fewer, right? You can have one and all these 4 together. So you can remove just one of these and you get one set. You remove this and you get another set. You remove this and you get a third set. So you have say 5 sets which are of size 5, right? So the computation of the sum becomes much faster. In the case of 2, you have so many numbers. So many, or if you take 3, again, you have so many subsets, right? So the input size depends on the value of not just n, but also the size k. So that is also one particular type of input where the size depends on these two factors. Okay, if you're not able to understand, just forget about it. What I'm trying to say is eventually, maybe these two things, or probably even these 3 things is something that if you have understood, that's enough.
Ma'am, hello.
Okay. Yeah.
Ma'am, I just want to say a thing. Here you have taken 6 elements are there, and we have to means k is equal to 2. Means so the number of possible subset will be 30, na? Means from these
6
n
choose
equal
2,
to
right?
6.
6 choose 2.
Yes,
So,
it will be 30, na?
you do the math, no? From a set of 6 and choose 2, right?
Yes, 6 to 2. Okay. So, but when when you have k is equal to 5, so it will be like a 65. So it will be reduces.
That's what, correct.
So
Correct.
yes, so you are
I'm not
saying
saying,
that
I'm not saying if it is k equal to 5, the value increase, the complexity, it's not increasing. The time complexity is not increasing. I'm saying if it is 5, then you can remove just one of these. If you remove this, you get a 5 element set. You remove this, you get a 5 element set. Like that, right? You have only 5 sets, no?
okay,
Sorry,
got it.
6 sets, yeah.
Means the algorithm, it depends on the algorithm, na? Means what we means in what way we are will
Correct. It
remove.
depends on the way, but then eventually you still have to, if you have to list all the subsets, that itself will take more time in the case of when it is k equal to 2, right?
Yes, definitely, it
Yeah.
will take
Yeah.
more time.
So all I'm saying is I'm not claiming that it will increase when k equal to k, when k increases. All I'm saying is it could be inversely proportional to k also. All I'm saying is that the complexity now depends not just on n, but also on another factor, which is k.
Okay, got it. Means you are saying that the n6 it is a input. N equals 6, it is a input. Also, it depends
N
on
and
the
k are
factor.
input. N and k are
Yeah,
input.
n and k are input. So definitely it depends on k also, because if the k value will be more, then it will may be easier for us, and if the k value will be very less, then it may be harder for us. So it
Correct.
definitely it will be depend on n and k both.
Correct.
Okay, man, got it.
Yes, that is another type of input. That's it. So you don't have to, worry too much about. I'm just trying to give you examples where you can define the size of the input based on the problem type. Okay. So that is sorry. Yeah. Now the next thing about is, yeah. Somebody wants to ask us something. Yeah.
Um, so,
Yeah.
ma'am, I just have a generic question. So in this session, we are going to next, like after the basics, we are going to cover the big O and omega of, of a function, right, ma'am?
Yeah.
So that is basically the most difficult topic of week 2. So that's
Okay.
why I just wanted to know about the
And
coverage.
unwinding also.
Sorry.
Unwinding.
Okay. So
Uh,
see. Yeah.
yes, ma'am. And for me, I have understand all the parts, but when I go to GRP to solve the programming assignments, but I am not able to do that. So,
Then I think you should work with your Python.
okay.
See. Coming up with algorithms or program logic, right? That is not something you can learn on a fine morning. It comes with practice. Okay, first of all, even then, if you have a problem, it is not necessary that you are able to solve it like within a given amount of time or anything. There might be something slightly tricky about it, but of course, the algorithm questions that we give are definitely doable. But what you should understand about these algorithms is that there are certain problems which cannot be solved, which comes categorized as kind of hard problems and all that. So that is a totally different kind of study. But all the problems that you see on this assignments, right? These are like doable problems, which with practice you will definitely able to do. So have you been participating in the live coding sessions and all that?
Yes, ma'am. Last time I have solved all the 6 questions.
So then I think practice is the only solution. See, for sometimes it comes intuitively, certain problems, certain solutions, it comes intuitively. Certain things might need a little extra practice. So see, for this session specifically, we are focusing more on the theory part of it. And the next session will be focusing on the coding.
Okay,
Okay.
okay. Thank you.
Yeah.
Ma'am, hello.
Yeah.
Ma'am, here you have said that the time complexity, it depends upon the number size of input, and also
Hmm.
you have said that here it depends upon the number of inputs, right? Like here n and k, there are two type of input are there.
Hmm.
Is that correct? Means it depends upon the number of input and also depend upon the size of input.
Now, what do you mean by number of input and size of input? I did not understand.
Size of input means, let's say n is equal to 6, but n can be larger, right? N can be
Yeah,
1000.
yeah, n can be 1 million. Yeah.
This is the size of input I am telling, and
Correct. That will be the size of the list.
yes, and here k is equal to 5 because k can be larger. This is also size of input. But here n is equal to means n and k.
See.
There are two inputs.
Correct.
So I am saying that it depends upon the number of inputs. I'm saying.
No, so if you say number of inputs, there are only two inputs, which is the value of n and the value of k.
Yes.
That is constant. The number of inputs is constant, the value of n and value of k.
Okay.
Value of n, how it changes, right? What is the big, I mean, how the complexity changes with respect to the value of n and value of k. The input as such is you are getting the value of n and value of k. Suppose you are saying that, okay, so the input can be a list which is of size k. But what I'm going to tell you is, say something like a list of numbers from say 1 to n, in which you have say all the even numbers or all the multiples of 3 or something like that, right? You can define it like that also, the input. Then you can compute the input by yourself, or the input list itself can be the input, and k will be the value that you will get as the other input.
Okay.
The input list, when it is given to you, you know the size n then, right?
Yes.
So it depends. It depends on. So for instance, in Python, you are just given a list and you can compute the value of n, right?
Yes.
So suppose you are given an input until say a character. You are somebody is keeping on entering numbers, say 1, 5, 10. They keep on entering until you enter say hash symbol. Until
Yes,
then,
like
that
while loop, how it works.
yeah, something like that. So that is also one way to take the input. All I wanted to tell you was it is not just dependent on the size of this input, but also depend on the other value of k.
Okay. Got it. Means
Got it, no?
yeah, yes. Means it not depends upon the only input of n. It also depends upon k.
Correct.
Okay.
Okay. Okay. So then the measure of complexity, right? So the measure of complexity, we have something like the best case complexity, average case complexity, and worst case complexity. So somebody wants to explain what is best case complexity?
Like ma'am, can I explain?
Yeah.
I am telling a situation. Let's say we have to search a number in a list, and that number I guess less on index 0. So that may be the best case. Means
Okay. What if you use binary search?
binary search, then it will give the result in first half. It will give the result.
For binary search, that would be the worst case.
Yeah, that may not be the best case. Yeah.
Okay.
Sorry.
Yeah.
Ma'am, in binary search, if
Yeah.
the middle index is the answer, like the element which we are searching, so that would be the best case.
Correct. That's correct. Yeah. So you when you say searching for an element, right, you have to specify the algorithm. We are specifying the best case, average case, and worst case for a specific algorithm and not for a specific problem. Okay. The analysis is now for a specific algorithm. So linear search has a specific performance. The binary search has a specific performance, right? So the case of best case is when it takes the least amount of time. The algorithm takes the least amount of time from among all possible inputs for that algorithm. This particular input will be, I mean, you will get an output in such a time that no other input will take time strictly less than this input. So this is one particular input or a subset of inputs, right? So you have you have this space, sample space, or whatever you call, of all possible inputs to this algorithm. And you have a subset of inputs which will give the output in a time which is the shortest among all possible inputs. So this is the best case performance. This is the best case best case time taken by that algorithm, right? So the particular input in which it takes the shortest amount of time. Okay. And this is dependent on the algorithm, not on the problem, as we've just seen in the case of searching. Okay. Is this clear for everyone?
Yes, ma'am.
Okay. Now average case. What is average case? Average case is you will look at all possible inputs, the time taken for all possible inputs, and you take the average of that time. That is this average case performance. So average case performance is very difficult to compute because, I mean, you will have to take some problem. I mean, you do some probabilistic analysis, find an expectation or something. But even otherwise, if you want to go through all possible inputs, you'll have to list all the inputs, and it's probably not a reasonable way to do. I mean, find kind of do the analysis for an algorithm. So whenever we talk about analysis of algorithms, we always settle for the worst case because of two main reasons. One is, it is quite possible that there are a number of inputs for this worst case is happening. So if you just settle for average case, there will be surprises. Okay. The second case is, you know for sure that I can give any input and still get the output within the time which is specified by this average case analysis. Okay. So we focus on the worst case performance of algorithms. What are the outputs that will give the worst output for us? Sorry, worst which takes the most amount of time. Okay, that's fine, right? Okay. Now I go to something called as the growth rate of functions. Okay, so this is where somebody was talking about difficulty, right? So what is growth rate of functions? So suppose you have, say, okay, you have, say, one for loop. Okay, so I'm just writing some pseudocode. Okay, so I'm just initializing, say, s is 0 for I equal to 1 to n, for j is 1 to n. Okay, s is assigned s plus 1. I want to print s. Okay, so sum. Now, how do you analyze this algorithm, right? So you look at the stepwise, what is the time taken? So in the case of these assignment statements, right, this kind of assignment statement, say in Python, you write it as s equal to 0, and even simple addition, say a equal to b plus c. These are all treated as taking 1 unit of time. Okay, these are like basic steps which take 1 unit of time. This step in which this for loop iterates from 1 to n, right? So in general, in Python and all, what it does is it will start from 0. It goes till n minus 1. When it reaches for 0, it will go inside and do all these things. For 1, it will do all these things. For n minus 1, does all these things. And then again, it comes to n and then it exits. So this is basically, this step will be running for n plus 1 times. Because it realizes, okay, now it has become n and it is not within the range which is given in the 4. So this runs for n plus 1. And here it runs for how many times? This n plus 1. Sorry, this run, it comes inside only till 0 to n minus 1, right? So this is n. So that is the n here. N into this for loop also has its own n plus 1, right? Which is this one. And this is again a constant function, which I mentioned here. This is also taking 1 unit of time. So this takes 1 unit of time. This also takes 1 unit of time. Right? So what is the total so this, as I said, this takes 1 unit of time. This takes 1. This takes 1.
Ma'am, so sorry to interrupt, ma'am. Why does it run for n plus 1?
Oh, sorry, this is not 1. Sorry, this is not 1. How many? This is this. For one step of this, this takes 1. How many times is this getting executed? Sorry, yeah. So somebody interrupted. Sorry, yeah. May know? Sorry.
It will be n times, na?
No,
I think, madam,
I come to that, but somebody asked something. I interrupted that.
Yes,
Sorry.
ma'am.
Yes, someone is asking why it is n plus 1, I guess.
Yeah.
This one, n plus 1.
Yeah. That's okay. Why n plus 1?
See, for loop, how do you write for loop in Python? For
I
Madam, it will go to
range-
only n minus
I
1,
in
right?
range of
correct. This is correct. No, so the range is from 0 to n minus 1, right?
Yes.
That's clear, no?
Yes.
So that is n.
Yeah.
But
run till end, right?
how you can just check in the internet, like how the for loop is implemented in Python. Okay, you will find that once it reaches here, it again goes here, increments it to n and realizes that that is not in what is mentioned in the range, and hence it comes out. So this for loop basically gets executed 0 to n minus 1 as you people think, and one more time before it realizes that, okay, it is not within the range, and then it exits.
When it is out of
Yes,
range.
ma'am. Yes. In the last, when it checks, then it comes out.
Yes, ma'am.
Correct, no?
Yes, ma'am.
You
You are
can see that
absolutely
you
right.
can actually search in the Google and figure out like why the for loop is executing n plus 1 times. Okay, just check it. So
But ma'am, why it is not in the case of J also?
no,
Here also it will.
because J gets executed only n times. Only for 0 to n minus 1 it comes to J. So that is
Okay,
this
okay,
n.
right.
This n plus 1 is for
Yeah.
J equal to 1 to n.
Yeah. Got it.
Got it, no?
Okay.
Yeah. Now this
Yeah.
statement, this statement, one execution of this statement will take 1 unit of time. So how many times is it getting executed?
N.
For n.
Ma'am, it
That's
will
it.
be n times, na?
N into n plus 1
N
times.
times.
N into
Sorry,
n
n
plus
into
1.
n plus 1 times, yes.
Why is it n
Into
into n
n
plus 1?
times. N into n.
Because ma'am,
See.
for every each iteration, and
So J equal to n.
Ma'am,
See,
it
J
should
equal
be
to n
n
minus 1, it goes inside. For
Yeah,
J equal
N
to
into
n,
n.
it does not go inside. No?
Yeah, N into n, right.
Yeah. For J equal to 0 to n minus 1 and J equal to 0 to n minus 1 only, this gets executed. The for loop, because it increments to that n and then checks it is not within the range, it comes out. But this s equal to s plus 1 will get executed only for the values ranging from I equal to 0 to n minus 1 and j equal to 0 to n minus 1. Is this clear?
ma'am, I got confused.
Clear.
See, this for loop is executing from 0 to n minus 1, right?
Yes.
N steps. So, but I have told you it will check once more. So you have an n plus 1. Is this clear?
Yes, it is clear. It will iterate n plus 1. Means
Okay.
it will
How about this one? How about this one? How many times does this get executed for j equal to 1 to n? And yeah,
1 to n, it will get
N
0
times.
to
it will get executed
n times.
n
Ma'am, n into n, right?
n into n plus 1. The j
N
statement, right? This j, okay, let me write it once again. For I is 1 to n, for j equal to 1 to n, this gets executed n plus 1 times, that is 0 to n minus 1 and one more time. But
Yes.
it goes to j to 1 to n
Yes,
only
ma'am,
for
it will-
these values.
Yes, ma'am. It will n into n plus 1.
This is clear, no?
N into n plus 1. Yes, got
So
it.
because of, so why did this become n here? For the same reason, this n plus 1 becomes n here. Because it is only going for 0 to n minus 1 inside. No, for n it is just checking and coming out. It is not going inside this one.
Yes. 0 to n minus 1, it will be n times.
It will go inside s to s plus 1. For the value of n, it will not go to s to s plus 1. So you will have this complexity n into n. Is this clear?
Yes, ma'am. So
So
as
J will not.
as into s is equal to s plus 1 will be executed for like n into
N times.
n
Ma'am,
into n into n times, na?
Yeah, n into n times.
Because n plus 1 is the means it is a checking, so it will be definitely n into n.
Correct.
Yeah, got it.
Yeah. Anyone else?
Ma'am, and J will not go like for extra step.
J will
That's
go for the
what it
extra
is
step.
going.
That is the n plus 1 here, no?
N plus
But
1.
for the last value of j, s to s plus 1 does not get executed. For j equal to n, s to s plus 1 does not get executed. S to s plus 1 gets executed only for the j values ranging from 0 to n minus 1. Once it reaches, okay, it has reached n, which is not within the given range, it comes out of the for loop. It does not enter the s to s plus 1 for the last value of j, which is n.
Okay.
Is this clear?
Ma'am, but when the n is large, the plus 1 will not matter, right?
No, it doesn't matter at all.
As per the
Actually,
time
I'll
factor.
just show you. Yeah, I'll just show you.
So can
So-
we take 10 raised to say minus 7, 10 raised to 7, sorry.
For what? No. Just one second. Okay, I'm just. Let us just finish this one step. Okay. So what is the time complexity? Is what we are trying to figure out, right? So this step, as I said, it's a constant time. It's just getting executed once. This printf is also getting executed just once. So I have 1 plus 1, 2. So this is from the s is 0 and this is from the print. Okay. Now I have the 4j equal to 1 to add, which is n plus 1. Sorry, I. This is the I loop plus n into n plus 1, which is the j loop, plus n squared, which is the s to s plus 1. Correct, no? So this is equal to 2 plus, okay, I'm adding this also to this. So you get a 3 plus n squared plus n squared. So this is equal to 2n squared plus 2n plus 3. Got it, no? That is the, so we are writing the time complexity or the number of steps in this algorithm as a function of input size. This is the input size. Okay. You're giving the value of n as input, right? Nothing else, you're taking it from outside. So the size of the list or the size n is what is going inside, right? Now when this value is, you are actually expressing the value of the time complexity of this algorithm as a function of n, and that is what you're getting here. Okay.
Okay, ma'am. Just one doubt, ma'am. We got this equation, ma'am. What does this signify? Does this signify seconds or any?
No. You should not. That is what I specifically started off saying. 1 unit of time.
So whatever answer we get in real numbers, it is like that much unit of time. From the
You can just say unit of time. You cannot say seconds, minutes, because if it's a supercomputer, it might take few microseconds or even much less than that, right? But if it is a regular machine, it might take much more. If for inputs of size, say 10 power 6 or 10 power 4 or something like that, right? So it's better to define this complexity independent of the computer architecture or the operating system.
Ma'am, once more this FN calculation of this 2n square plus 1. Please once again explain this one. How to
this step?
Yeah.
Okay, so for
FN,
I in range n, right?
Yeah.
For j in range n. Okay, this is s is assigned s plus 1. We are initializing s here first, and finally
0.
we are printing. Yeah. Okay, this is probably not Python. Okay, this is SC. Okay, I will just erase it, just so that I don't want to confuse you.
Can you mute yourself, Srikant?
So this is s equal to 0, s equal to s plus 1, and you're printing s. Okay, so this is the steps. Now I'm saying this step will take 1 unit of time. Okay, now I'm going to skip that unit of time. Okay, how many steps? That's all what I'm looking at. Okay, this is how many times? 0 to n minus 1, which is n times, plus one last time checking if getting to n and then realizing, okay, it has to exit. Okay, is this clear?
Yes, ma'am.
Then you have 0 to n minus 1 again here into what you're getting here, right? This one. No. Yeah,
n
so
into
this
n
is
plus 1.
Yeah, this 0 to n minus 1 is coming from the I, right? When I is 0 to n minus 1 is when we are going to this step. So you have n in this thing, and then the whatever is applicable for I loop, so the for statement of I is applicable for j also, and we get another n plus 1 here. Is this clear? Then finally we have just one more unit of, sorry, not one more unit for this step, and this step gets executed how many times? N into n times, because the s equal to s plus 1 will get executed only for I equal to 0 to n minus 1 and j equal to 0 to n minus 1. When j becomes n, it exits that for loop. When I becomes n, it exits the outer for loop. So s equal to s plus 1 basically gets executed only for I equal to 0 to n minus 1 and j equal to 0 to n minus 1, each of which is like n into n, which you get as n squared. This is again 1 unit of time. Is this clear? Somebody was asking me. So f of n.
Yes, ma'am. Yes, ma'am.
So now it is just simple addition. 1 plus n plus 1 plus n into n plus 1 plus n into n plus 1, which is 1, 2, 3. So you have 3 constants
Okay,
plus.
got it, ma'am. Okay,
Got it,
thank
no?
you.
Yeah.
Talking. Thank you.
Yeah. Now let us go back to the
Thank you, ma'am.
Huh? Sorry?
We will ignore the constants, na?
Yeah, I'm just coming to that. Yeah. So now we have this function, right? So asymptotically, right? Again, I come back to that asymptotic word. What I mean by asymptotic is when the n tends to infinity. This is the n is the input size, whatever we are defining as the input size, right? When n tends to infinity, how is this algorithm going to behave? So suppose this n squared is something like 10 power 6. Sorry, n is something like 10 power 6. Then this factor becomes what? N squared becomes what?
10
Correct,
power
no?
12.
Yeah.
10 power 12.
10
And
Yes,
this
ma'am.
n is 10 power 6. So you can only imagine this is far, far bigger than the 10 power 6, right? So now this is the dominating factor here,
Yes,
dominating term here. Which one? This n squared. So to simplify our analysis, what we do is we discard all the lower terms. Only the highest term we retain it. Only the highest term in this expression is what we retain to express the asymptotic complexity. So you have to understand that word specifically. Whatever we are studying is asymptotic. When I say asymptotic, it's the performance with respect to n tends to infinity. So as the n becomes higher and higher and higher, this lower terms kind of become ignorable as compared to the highest term, and hence we focus on the higher order term only. Again, you have, say, there is something for n squared and there is something for 2n squared, right? Probably, no, I will come to that. That c into g of n, that I'll come to that. Okay. So, yeah. Okay. So, if this is n squared, and there is, 2n squared. So now I have, say, f1 of n equal to 2n squared. And there is another algorithm for the same problem I have come up with, where f2 of n equal to 5000 n. Now you can do an analysis of which will do better than the other. Say, for instance, at what point does n square start to, so this will be something like, the graph will be like, you have this n squared might go something like this, right? N squared is a parabola, right? Quadratic.
Yes,
After
ma'am.
a certain point, this n squared will start to dominate the bigger one. This point, right? This point and this, the value of, this is the value of n, this is the value of t. So this is the input size. Input size keeps increasing, and this is the time taken to execute the code that keeps increasing in this side. So for n, for 5, oh my goodness, my straight line is, sorry about that. I'll just, 1 second, okay. I'll draw it again, sorry. Yeah. So this is the n, or rather 5000 n, let it be, okay? And my n squared is coming from here, 2n squared is coming from here, and at some point it crosses this. So what, let it be some value. You can do the analysis and figure out what is it. This is supposed to be a parabola, okay? Let this be some value of, say, this is the x-axis, which is the size of the input, and t is the time taken to, time taken for that algorithm to give that output for that value n, okay? Now, at this value, say you have, say, n0, it is very clear that this 2n squared takes much more time than what is taken by the 5000 n. See,
But
you
that's
don't,
just only after n0, right? Before n0, the 2n squared algorithm is
correct, that's correct, you are right. But what are we looking at? We are looking at the value where n tends to infinity, right? You're looking at the analysis where n tends to infinity. So when I say n tends to infinity, please don't think that n becomes infinity. I'm saying like very large values of n. That's the whole asymptotic complexity is about, study of this asymptotic complexity, right?
Yes, ma'am.
Got it, no? Yeah. So now we say that, okay, this f2 of n, right? For some constant, say I'm putting it as n0 into 2n squared. So here, this f2 of n is going to be less than or equal to n0, some value. I mean, it need not be n0, can be some other this thing, but it is going to be less than or equal to this function. Sorry, not n0, some constant c. N0 is some other value. Okay, I'll tell you. For all n greater than or equal to n0. Is this correct?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Ma'am, I have two doubts here.
Ah,
So the first one is like, why is f2n 5000, and like there could be many different functions possible which are less than 2n square, right? Like which
yeah,
are also
possible.
not straight line after a certain
Like,
n. Like how did we come up with the 5000 n?
no, I'm just trying to show you what is this O notation. That's the motivation.
Okay. And the second doubt is, madam, like,
Hmm.
so the function directly is less than or equal to 5000 n, madam. Why is there a constant multiplied c into 2n square?
So even if C is there or not, like even if it starts from here itself, right? If it starts from here, like this itself, if it is just going up, there is no constant needed. Even with simply that function itself is doing it, it is still okay. It's still dominating. In that case, you can put it as C equal to 1 or C equal to less than 1, whatever, right? But it is possible that it goes after this certain point, it goes beyond that. So it could be, there could be a multiplication factor which comes into there. It is possible is what I'm saying. There could be a C. If you want to avoid the C, that is okay. It will still work. Whatever I'm explaining will still work. But if it is a C, if I totally ignore C and try to explain to you the O notation, then if there is a C, you will not be able to accommodate it.
Okay, ma'am.
Okay, so let us assume that for some constant C, okay, you can actually find out like when this 5000 n is going to behave better than the 2n squared, okay, for some constant. You can just figure out this constant for some value of n greater than n0. You can just
Ma'am,
do it as an exercise. Sorry?
Ma'am, may I have one question?
Yeah.
Here, what we mean by the dominating? This is a time exactly. Fn is giving the time taken by the execution.
No, it's okay. So here what I meant by dominating here is, see this 10 power 12, if it takes so much of time, then the time taken by this factor, right, this 3n, that will be kind of negligible is what I'm saying.
Yeah, dominating
that is what I meant by
it is
dominating.
It is taking more time.
Yeah, I mean, that is exactly what I'm trying to say. It's taking time only, but
because we have calculated Fn as the time taken by the execution of that for loop or two loop, nested loop. That is the time taken by the execution, and Fn gives the time taken, na ma'am.
yeah, okay. So rather than time taken, you can look at it as number of steps. For every step, we are saying it is a one unit of time.
As a number of operations.
Yeah, number of operations.
Number of operations are more in F1, right? In more than F1 is taking more operations than F2. Is it so?
Yeah. So until this value, right? Until you reach n0, the time taken by n squared is less than the time taken by 5000 n. Is that correct? Because that's what this graph means, right?
Yeah. Condition F1n will take higher time than F2.
No, my doubt is different. Graph I am understanding clearly, ma'am. I am understanding dominating means in the terms of dominating. Dominating means it is taking more time. Means dominating means it is taking more time. It is less efficient.
No, dominating I mentioned with respect to this 2n squared plus 3n
yeah.
plus
That
3,
is,
right? So here if it
yeah,
is 10 power 12, then this is far, far greater than 10 power 6.
yeah, yeah.
And hence,
Order is dominating. So order of this that is dominating, right? Function order of that function is dominating, right? Is it so?
okay, you can probably ignore the word dominating if it's confusing for you. I
Okay.
mean, it just came out
Okay.
of my mouth because I thought that
Okay,
probably
okay,
conveys
okay,
better.
okay,
So you
okay,
can just
okay,
ignore
okay.
it.
And
That's fine. Yeah,
second doubt,
yeah,
ma'am.
yeah.
Asymptotic complexity and time complexity are same or different?
No, no, see, time complexity can be analyzed in many ways. We are actually looking at this asymptotic complexity, which means when n tends to infinity. That's it. You can do it when n is like, when both values are n equal to 100 or like, n is less than a particular value, then probably you
Okay,
might
that
get
is
a
different.
totally different input. Yeah. So generally, whatever analysis we are
Okay,
doing
okay,
in this course, it's asymptotic complexity, where, n tends to infinity.
okay, okay, okay,
Okay.
okay. Thank you,
So
thank you,
now,
thank you.
yeah, now from this graph, it should be clear that this whatever might be this constant 5,000, right? Unless it is something like 1 billion or something, this 2n squared will be a dominating value as compared to, sorry, again, I'm saying the dominating, excuse me. So n squared will take more time, or it will have more, it will take more time to execute as compared to the 5,000n.
Yes,
So,
correct. Okay,
yeah.
okay.
So in that case, we say that this F1, not, no, I did not hear. Is that? Did
No,
anyone
ma'am.
ask you?
Please
No?
continue.
Okay, yeah. Okay. Sorry, just one second. So let us have, say, two functions, f of n and g of n, just like we have defined the f1 of n and f2 of n, right? So why I'm again going to f of n and g of n is you will be able to understand the lectures if I use this. So that is why I'm again going back to f of n and g of n. Okay. Now we say that f of n is equal to O of g of n. See, this condition is there, right? The f of n is less than or equal to c into g of n. Again, this condition for all n greater than or equal to n0. This is the crux of O notation, where, so there exists some c and n0. So this symbol means there exists, okay, just so there exists some constants c and n0 for which f of n is less than or equal to c times g of n for all n greater than or equal to n0. This is the definition of O of g of n.
Ma'am,
Is this clear? Yeah.
ma'am, this C is very confusing for me.
Ma'am, in the
Uh,
I mean, I cannot understand like this C, like how this C is fitting in this equation. If you can explain that again, I cannot understand it. I was not able to understand it in the lecture also.
okay, so for that, what you have to do is in Sir's lecture, Sir is actually giving this 5,000 n cube and 5,000 n squared, right? No, what is it? Do you remember that example Sir is giving to explain the C and G of n and all that? Have you seen that? Okay, let me get the slides for
Yeah,
that.
madam, it is n cube and 5,000 and square, I think.
Simply n cube and 5,000 n squared, right? Okay.
Yeah.
So n cube and 5,000 n squared, right? So suppose n equal to 4,999. Okay. Then you have 4,999 into 4,999 into 4,999, correct?
Yes, ma'am.
Here you have 5,000 into 4,999 into 4,999, correct?
Yes, ma'am.
So once this n value becomes 5,000, so probably I'm explaining the n0 right now, not the c. Okay. So once this n becomes 5,000, both are same, is it correct?
Yes, ma'am.
And for whatever value comes after that, right, whatever value comes after this, n cube will dominate this. Sorry, n cube will take a higher.
Yes, dominate. I understand that. Yes.
This is fine. So probably I'm explaining that n0, right, not the c. Okay, so you want an example where I can take a c and Let me think about it 1 second.
I think ma'am, C is a constant and it could be any value, right?
Yeah, you can actually. So all you are saying is there exists one such C. If you can come up with one such C and an N0, then so what? Somebody was asking about C. No, can you tell me what happens if I remove the C? So what you're saying is the C required at all? Why don't we simply say f of n less than or equal to C into g of n? Is it?
Ma'am, one thing can I say?
Yeah.
Ma'am, here, like say, if NQ and 5000 n square is there, na? So if you'll take any C, let's say any C, let it be 5000 or any one or anything. So obviously that 5000, let's say it is 5000 NQ. Then obviously 5000 NQ will be greater than means 5000
Sorry, you're
n
not
square.
audible.
Means whatever the C value you will take, it always be greater than. Here you have taken n is equal to 4999 and C is 1. So this is the condition of n0. But if you are taking any C, means C will be 1. Here you can take, means here it is 1.
Okay,
If
got
you
it.
take more than C,
Got it.
then it will definitely greater.
Okay, got it. So yeah, I understand what I can try to explain that way. Okay. So you have the 5000 n and 2n squared case, right? This is f. Say this is f of n and this is g of n. Okay.
Okay.
Is this fine? Okay. Now we want to say that f of n is less than or equal to g of n into c, right? This is what we want to figure out, right? So, but as I have seen, for if you have, say, 1 second. This is the 5000 n and this is the n0, right? Correct, no?
Ma'am, N0 is 2500, right?
5000.
Yes. Yes, ma'am.
And ma'am, in both the, both the cases, it is 2500.
It is 500, na? N0 will be
5000 divided by 2. That is
It's 2500.
sorry, 2500.
2500, yes. In both the cases, even in the 5000 n cube and 5000 n square case.
Okay, so you can. So
yes.
Hi.
Because it doesn't have anything to
5000
do
is
with an n cube and n.
Yes, it does not have anything to do with that C value. It is 2500. Does not matter. Does not depend on C.
yeah, this is what you meant, no? Beyond this, whatever comes for 2500, like 2501 onwards, this will be larger, right? That's what you mean.
Yes.
No, this will be larger. Sorry, because this will also become 2500. This will also, this alone will be changed. Okay, got it. Yeah, so that's what the n0. But you are okay. So I think we kind of got distracted. We want to figure out the C, right?
The other functions, ma'am.
Sorry.
The other functions n cube and 5000 n square.
Yeah, then also the n cube will be greater.
500, right?
No, that I told you, right? 5000 is that value, right? So beyond that, what happens is here, you have 5001 into 5001 into 5001. Here it will be 5000 into 5001 into 5001, right? Because this 5000 doesn't change. This becomes 5001 into 5001. This becomes 3 5001s into. So from this onwards, the n cube will become a larger value.
Yes, ma'am. Got it, ma'am. Thank you.
Got it, no?
Okay, so sorry, madam. So C is 5000 here.
See, actually,
C here is actually 1 because NQ is greater.
No, N not is 4999 for
no,
suppose.
f of n equal to n cube. Sorry, f1 of n equal to n cube, f2 of n equal to 5000 n squared. Then n is not, C is not 5000, right?
Yes, C is 1 because
F2 is very much part of, 5000 is very much part of the definition of F2n, right? F2 of n. Only if once you remove the constants, right? So if you have, say, g of n, so, okay, so.
I think C is 5000, I thought, like, because
no.
there is an n naught value. There is an n naught
value
value which is there, which we substitute in the place of n, and there is a C value. Like if we take any other value, 4999C or any other C, so
So
that's
let
what I
me
thought.
just check if Atul is on the call. Atul, are you on the call? Okay, Atul is on the call.
Yes, yes, yes.
Yeah, do you want to give some input on that, like the C and N0? Do you have an example where?
So okay, I'm connecting with my tablet. So 1 second. Yeah, wait for a minute.
Yeah, sure, yeah.
Definitely,
So we want an example. That's the.
Ma'am, should we only be worried when n cube passes the other function?
No. See, what we are trying to say is that which function will take more time when n tends to infinity. That's what we are trying to
Yes,
figure
we
out, right?
always means, ma'am. One thing I have to say, like we always have to find the things at n is equal to larger. So we don't think about that n0 thing. It is not relevant to us.
No, that is fine. But how do you define the O notation, right? The standard definition of O notation is where you have to show that there exists some constant C and N0.
But
Yes, ma'am. We have to find n0, no? Because n0 is a threshold value.
Yeah.
Yeah,
No, I mean,
but we have to find that f of n and g of n first. Then we have to proceed for that. So
See, we also have to find that from which point f of n is in.
The actual problem was regarding that C means one side saying that it means it is not able to understand that is a C. I am saying that whatever be the value of C, it does not matter. It will never be changed. That C into G of n always be greater than f of n.
no, that is not correct. That is not correct. Okay, I just think I may have an example. So something like, say, you have something like 3n and see f of n is this one, and g of n is, say, 2n squared. Now,
Ma'am, can I add something?
Yeah.
In this case only, where n cube and 5000 n square was being compared, if let's for example say that we are trying to get that asymptotic relationship of O, where C dot G of n is being compared. If I take C value as 2, then I'll get the same value for which the relation changes as 10,000 instead of 5,000, which was previously being given. So if I take C as 2, then it becomes 10,000. If I take C as 4, maybe then it becomes 20,000 when it will be compared. So if I write it like that, 10,000 cubed is equal to 2 into 5,000 into 10,000 square. I mean, that will become the point where it will become equivalent. That graph will become equivalent. So in a way, what Debashish is trying to say, if I'm not wrong, that for any value of C, Gn can be greater than Fn for any particular value of C. In our case,
Yes, ma'am. So
one only.
just the n naught changes. If we change C, the n naught changes. That's what we are.
N naught changes also. Yeah, that's what I'm
Yeah.
trying to say.
Yes.
Yeah.
Yes.
So
I don't think
I'll stop
that.
sharing, Atul. I'll stop sharing it.
Okay.
Yeah.
Can you turn off your mic? Someone is, I think. Yes, Srikanth. Okay, sir. Yeah. So, ma'am, can you repeat the equation which you have written for the for loop function?
Yeah, f of n equal to 2n squared plus 2n plus 3.
2n square plus 2n plus 3. Okay.
Yeah.
So this is the actual function. Basically, we have computed from the code. Okay. So now how we can represent this function with the big O notation. So basically, there is a condition for big O notation to represent the big O notation, which is which ma'am have already written. So this is the condition fn. It should be greater than equal to there is one C Gn. Okay, and for all n not sorry n is greater than equal to n naught. So how we can prove this? So basically we have to find out the Gn function from this Fn function.
So how we can convert this? How we can find out this? Find out the gn function from this fn function. So we basically we can prove. So we can write in that way 2n square 3. Okay. So this is the actual function. Can we so can we written in that way? So if we take n, if we take
sorry to interrupt, that fx is greater than or equal to, is it greater than or less than, sir, c dot gx? Because it's a worst case, right?
It is a less than, I guess.
Yes, ma'am, I have also written less than.
So obviously less than that would be, I guess.
Okay, 1 second, I'm checking.
Yeah, for big O it is less than or equal to. Yeah.
Fn is less than equal to?
Yeah, less than. Yeah. If f of n equal to O of g of n, then f of n is at most c dot g of n. Yeah.
Okay.
Because c of n will be above, right? The in the graph c dot g of n will be above f of n. So it will be less than or equal to. Yeah.
Okay.
It will be upper bound.
Yeah, so we are calculating the upper bound here. So this is
upper bound.
Yeah, gn we are calculating here. So
for big O it is upper bound, omega is the lower bound, right?
So for example, if we can so we can write like that 2n square plus 2n plus n. Okay, so if we are taking n equal to 3, so can you say that this condition is true?
How can we write n here?
Actually, we are calculating the n naught value. So we are just processing the sequence to find out the gn terms.
Yes,
okay?
it is true. It is true.
Okay, it is true. Okay, if we are taking n equal to 3, so we can write in that way. So this is correct. So 2n square plus we can write 3n. This is correct. Now after that, for comparison to this equation, can we write if we take n is greater than equal to 3n. So n square is greater than equal to 3n for this. So we can we write 2n square plus n square here for this value?
Yes, it is true. It is true.
Hello.
Yes.
It is true. If we write n square is greater than equal to 3n and just we put so if we replace by 3n by n square, so for every value of n square is greater than equal to 3n, so always this part will be less than compared to this part. It is true?
Yes, sir.
Okay. Okay, so now we can write this sequence in that way. So 3n square. Okay. So now we can simply write that. So we have following this sequence. So we can simply write that 2n square plus 2n plus 3. It is less than equal to 3n square. For what value? So we can calculate the value of n naught from these two conditions. Where one condition is n equal to 3, and second condition we have taken n square is greater than equal to 3n. So what are the common value which will satisfy the both condition? If we take n equal to 3, okay, so this condition is also satisfy the second condition.
Yes, sir.
Yes, sir.
Yes.
Correct. So we can take n equal to 3. That means if we take n equal to 3 or greater than 3, so these both condition will be satisfied, and we can so these condition will also be satisfied. So which we have proved. So that means for n equal to 3 and n is greater than equal to 3, we can say that n is greater than equal to 3. This condition is always be true. So here we can, so this is a actual fn function, and this is less than equal to this. We can compare by cgn. Okay, so here c equal to 3, gn equal to n square, and n not equal to 3. So these all values, so all required value we have calculated, we have proved, and then we can directly written that fn equal to big O gn. Okay, so what is gn? So big O n square. So this is the way to written the complexity in the term of before notation.
Sir, I just have one doubt.
Yeah.
Sir, here I am actually that is the thing I am not able to understand. Here it is C is 3. So I means I am saying that means for n is greater than equal to 3, so C value is 3, or any value of C we can say that this is possible.
Not any value. So if we take C is lesser than so for example, if it takes lesser than 3, so maybe this condition will not true for n, n is greater
Sir,
than equal to
n
3.
is greater than equal to 3. We are getting at last means if we are putting the condition n is greater than equal to 3.
So for example, if you are changing the 3, if you are taking any value of C, definitely this n naught value will become changed.
Yes, I am saying that means here we are initially means assign the condition that n is greater than equal to 3. That's why we got the C value equal to 3.
Yeah.
So, but if we change C value, then obviously n naught value will be changed.
Yeah, that will become changed, and that we can also
That
consider
means
for
it is
bigger
always
notation.
correct that f of n is less than C of g of n for any value of C, because only the n naught value will be changed, but for any value of C, there will be a present of n naught.
Yeah, so actually if we take, for example, if we take put some another value in this equation, so in the previous equation when we are taking this value, for example, here we can put some different value like n square is greater than equal to n. So this condition we can also take for this situation, and then so definitely this C value will become changed, and n naught value will also become
Yes,
changed.
means here we are applying the condition n square is greater than n. We can say I can say n square is greater than 2n or anything. That's why means it will change the value of C. So at last I am trying to say that f of n is less than C into g of n. It is always true for any value of C. Is this correct or not? I am just asking this.
Any value of C.
Yes, sir. Like means there exist infinitely many
Yes,
functions which
infinitely
are
many function n
above
square is
the
So
greater than
Debashish, see, n is the input size, right? Is it correct?
yes,
And n0 is also input size.
Yes, n0 is
So
also.
suppose you are saying that the n becomes, the one becomes better than the other, or I mean rather it takes more time than the other, and some say 10 power 4 or 10 power 6 for any value of C, right? At the same time, if you put some value of C and the n0 can be a smaller value, then you have a better bound on that, right?
Yes. Yeah, I got it. Means
You can balance the C and N0 is what I'm saying. You can balance between C
yes.
and N0
No,
so that
I got it. It means we have a condition on n0. Means if n0 means we have to deal with the maximum input size.
Correct.
So definitely n0 should be with what maximum we are taking.
I think in more mathematical term we can say that for any given C greater than 0 there exists some n naught or that
Yes.
thing.
In mathematical term, that is true.
Yeah.
Yes, that was actually.
Yeah, so actually we are try to proving these things. So after n naught, so after any n naught value, so always this CGN part will always be higher than this Fn part. Actually, we are trying to prove this. If we can prove this, then we can write the complexity with bigger notation.
Sir, whether these Fn should be solved mathematically or this trial and error method, because we have put the value n is equal to 3. This is a trial and error method. Whether we can solve this without putting the value of n is equal to 3?
no, that may not be possible all the time. We will have to do some trial and error, especially
So
if it is very complicated functions, right? Involving
Okay.
square roots and log n and everything. It will be tricky, but we will still have to do that.
I think the intuition should be mathematical, but the application should be a bit of computational.
Correct. And not just that, that is possibly why we are ignoring the lower terms, right? So we just have to deal with 2 and the trial and error becomes easier, right?
Means the trial and error it will be easier. We put some value so that the function becomes greater than or less than equal to, right?
Correct. Yeah.
Okay.
We can either get an upper bound or a lower bound or whatever we are looking at, right?
Okay.
Okay, yeah.
So, okay.
Yeah, thanks, Sadhu. Thank you very much. Yeah, I think I will start sharing.
one question, ma'am, if you can
Yeah.
just cover that the rest
Yeah,
of
yeah,
the
yeah.
question sometime,
Yeah.
which is big O and theta and omega, and then there's one question in the graded assignment. I mean, obviously we don't want you to solve that for us, but generally an understanding between worst case, best case, still not very clear. What does it mean? Average case. When should you look at what? What is the interrelationship between them? It's not clear at all. If you can just help us with that a little.
See, don't get confused between best, average, and worst, and O notation theta and omega. Okay, so this can be a little confusing. Omega, the big omega, right? Okay, I'll just explain that, the big omega notation. So what we saw now is a big O notation. Now we are looking at the big omega. Big omega is just the opposite of what we saw. So f of n is bigger than c into g of n for all n greater than or equal to n0, n greater than or equal to n0. Okay, so this is the definition of the omega. What it means is that for every value of n which is greater than or equal to 0, the f of n will be above c dot g of n, which means that the g of n is something like a lower bound.
Correct.
Got it, no? That is clear,
Yeah.
right? Just
Correct.
like the O notation is the upper bound, the omega is the lower bound. Correct? Now, theta is the case where you have something.
Both of them are the same. When like it's rare
Yeah, you
cases,
have a
but
one constant, say C1, which is less than or equal to f of n, less than or equal to C2 dot g of n. Right, so graphically you have something here, and in between here is what you have the f of n. Correct, no? This is C1 is less than f of n, yes, C2 is less. Now, how do you relate the three, right? So suppose a function has the worst case complexity also n squared and the lower bound is also n squared. Then we say that it is tight. We say that you cannot have a better, I mean, for every input or for the lowest time that any input is going to take for this, right? That is going to be n squared. Say for instance, in the case of, I don't know whether you have seen the selection sort algorithm. Have you seen the selection sort?
Yeah.
You've seen that, no? So see, in selection sort, the best case, average case. So here you can see, okay, maybe this is not what I'm, okay. So here, not the selection, this is the insertion sort. Yeah. So if you can see here, even for the best of, okay, where is my drawing tools? Okay, let me try writing here. There's importance. Okay, this.
Ma'am, I had a doubt.
One second. Let me just finish this. Okay, let me just finish this. Sorry. Okay, so you can see here, this means that the best case is O of n squared, meaning even for the input that takes the smallest amount of time, it will take n squared comparisons. So here it is the algorithm this is omega of n squared, the complexity of the algorithm. At the same time, the any input, right, it does not take more than n squared, which is O of n squared. So this is kind of tight. You cannot find an input where it will take less than n squared and there will not be any input which will take more than n squared.
Basically everything is n squared.
Within that. Then you say that this is a theta of n squared algorithm. This is a tight bound.
But so best, average, worst have, like, I can't correlate them with big O and theta.
No, average, don't worry about it. Average is different. See, best is, what you're saying is that is kind of the input which takes the shortest amount of time. So for every other input, it will take at least so much time, right?
Yeah, so that can be related to omega.
Yeah, something like lower bound, correct. But I'm telling don't take the average case into it.
Okay.
The worst case is where this particular input, which will take the maximum amount of time from among all possible inputs to that algorithm for that particular value n or whatever, right? So I'm saying where n is constant. The value n is constant, but the list can change. Say you have numbers.
Yeah, I understood.
Got it,
But
no? You
it
have
could be
10,
already
14,
sorted or
yeah,
semi-sorted
correct,
and
correct,
things
correct.
like that.
Correct, something like this. Or it could be 10, 14, 16, 21 already, right? For any of these inputs, it's going to take n squared. In that case, it is a type bound. That is a theta. Okay, so that is not to be confused with the average case. Okay, yeah, somebody else was asking something, I interrupted.
Yeah, ma'am, Navika, my doubt is already cleared in the explanation. I just wanted to ask that does big O notation implies worst case scenario and
Yeah, so just imagine, no, what do you mean by O? What do you mean by the big O
it's like
notation?
the upper bound. It's like
It is like the upper bound, right?
yeah. If Fn is O of
No,
Gs, Gn is the upper
exactly.
bound.
That's also, yeah, that's the same thing we are going to refer by saying the worst case also, right?
Yeah. And similarly, our omega
The
is
lower bound also.
Just out of curiosity, why is it called O? It could have been called anything, but why is it
Yeah,
called
I have no idea.
Okay.
Maybe there is some origin. Maybe you can just read about it.
Try it, but anyway, thanks.
I guess it's from the Greek alphabets, omega, theta,
That
everything
is
coming
clear,
from
but
Greek, but O
why
is slightly different.
why big O?
And it's actually, you say it is this big O, not even O. This is actually how you say that, big O.
Means big O means it will take highest time, right, no ma'am?
Correct. Worst case.
In the literally meaning it will take highest time, and omega it will lowest time, and that is theta is the average time, right?
Sorry, come again?
No, theta is not the average time.
Big O, see, Big O doesn't, okay, so let me clarify this. Big O doesn't mean that there is an input which will necessarily take that much. That is one confusion between the worst case and the big O. Big O means that no input can take more than this. That's all what we are saying. We are not saying that there is an input which will take this.
Yeah, that is worst case.
Because that's where we are able to say whatever is O of n squared is also O of n cube, right?
Yeah.
Because there may not be an input which takes n cube, but it is still O of, because that is one upper bound. But again, we generally want to find the lowest upper bound so that we can have a tight bound. But still, O notation still works for O of n cube, O of n power 4, etc. Similarly, the omega also. You're saying it will take so much, but it is possible that you can get a better greater lower bound.
Okay. That is.
Yeah. Whereas the case of best case and worst case, in this case we are specifically saying, okay, there is one such input where this is possible. In the case of worst case, there is
that will depend. That will depend on the number of size of the.
Correct.
Size of the number.
The input combination also, like there is one particular or maybe one or more combinations where the worst case can happen. Say for instance, in the case of insertion sort, right? If this list is already sorted, you get an O of n. That's the best case, right? Got it, no?
Oh, yeah.
So, but the lower bound, you can say that it will at least take omega of log n, right? It will take at least log n for sure, because it will take at least O of n. So that's the difference. So you cannot confuse. You can just try to understand using this analogy, but it's probably not the right to exactly say that this means that. I mean, the worst case means O, and you can try to understand using that, but big O means much more. Like it's like you can have a much higher function. It's still the big O notation is still correct. Okay, but whenever we define the complexity for the algorithms, we define the lowest upper bound so that we get a tighter bound for the complexity. Okay.
Yeah, one or two examples we will do, then it will be clear.
Yeah. Okay. So what I was thinking is, okay, so this is the examples that we did. Yeah.
Ma'am, I had one doubt. Can I ask? It's just based on complexities only.
Yeah.
So, ma'am, like in the video, Madhavan sir had mentioned, it was lecture number 3, he had mentioned one example wherein he said that if we let's suppose we are checking duplicates in a list, right? So we'll be using the naive approach, wherein we would be using two loops, and then with each element we would be comparing it with other elements. Yeah. So the worst case scenario would be order of n square. That is, we don't find any element, we're just out of the loop. So that's the worst case scenario.
There are no duplicates, right? That's what you mean.
Yeah, there are no duplicates, and we just come out of the loop. So the condition is false and we're out. But there could be a best case scenario as well, wherein maybe the first and the second element, that is maybe L0 and L1, are duplicates, and we just find
so if you want to find if the question is find at least one duplicate in this, then you can find that. I mean, that's the best case, right? For I equal to 1, j equal to 1, the 1, that first two elements are the same. Then you are kind of done if you're asked to find only the first duplicate. However, if the question is to find all the duplicates, right? Then you have to still go through both the. Yeah.
So, ma'am, let's suppose if we just want to find the first one only, like just one duplicate. So then what would be the complexity in the best case scenario, where only
constant
the first
time, right? Constant time, no?
Order of 1, right?
Yeah. The first for loop will be ones, the second for loop will be ones, right?
Would be ones. Okay. That's what I wanted to ask. Okay, thank you.
Say, for instance, in the case of linear search, right? You get the element, the first element itself is the element that you're looking for, right? Then that is just one comparison.
Yeah. Got it. Thanks.
Okay, so now we look at some simple complexity examples. So here, in this case, you have, say, this is, as I said, this is an assignment statement. It's an assignment statement which just takes one, this is just one step, another step, another step, another step. So this is just 4. So whatever takes this, any constant amount of time, right, which is not dependent on the size of the input, we represent it as using this. This means constant time. Okay, for those people who are not aware of this notation, O of 1, it means it's constant time. What do you mean by constant time? It means you are not, the time needed to run this algorithm is not dependent on the input, the input size or the number of inputs or whatever.
Ma'am?
Okay. Yeah.
Ma'am, in this case, can we say that this is tightly bound, or like will that apply in this case, like tightly bound?
Yeah, so here best case, worst case, everything is the same only, right?
Yeah, so we can say that this is tightly bound.
Yeah, because the best case and the worst case are the same, no?
Are the
same. I think I'm not able to hear you properly. Little bit I'm able to hear you. Can you speak a little louder?
Yes, ma'am. I understand.
You got it, no?
Ma'am.
Yeah.
Like big O of 1 is 4, right? Because each step takes 1 unit of time.
Yeah. Okay. No, not that. Sorry. So big O of 1, because see, we told you, right? We are ignoring all the constants.
Oh, yes.
So if you put it as 100 n squared, right? You are just going to say it is 100.
Yes.
So this has only constant. So instead of just putting O of nothing, you will put it to simply 1, because it implicitly means 4 into 1, right? So this is the notation for constant time.
Okay.
Got it, no?
Okay. Hello, ma'am.
Yeah.
Ma'am, can you say once more, means constant time, what does it represent? It means
constant time is for any input. See, here it is actually not taking any input at all, right? But even if you take, say, I equal to some input, right? You are not using the I at all. Correct? So, but still this algorithm takes only constant time. It's not making use of the I, it's simply taking some input, or it could just print the input, whatever. But it's taking only constant time.
Let's say you have to return the first element of a list. However big the list is, it doesn't matter.
Yeah, if you know the index of the element that has to be written, it need not be the first one. It could be, say, the 10th element, last element, or whatever, right? It's a constant time operation. Okay. So
it is not function of any variable actually.
Yeah. So again, I want to make it more clear, but it again depends on the internal implementation and all that. But if it is something like an array-based implementation where you have this direct access to each index, right? That's when it becomes a O of 1 operation. Otherwise, you just have to go through. If it's a linked list, then you have to scan through the linked list, and probably you have to have that O of n again. But assuming again, it is depending on the intent. So don't want to confuse on that. But let us settle for the first element itself. Then that is kind of the same for whether it is a linked list or array or whatever, right? Yeah.
Wherever there is a constant, we will just write big O is 1, right?
No, not wherever there is a, see, this is a constant,
Yeah.
Wherever there is an n, a function of n, we will retain only the function of n. But here, there is no function of n. Whatever be the input, the running time or the time complexity is not dependent on that input. In that case, it is constant time. It will take the same number of...
Even in this example, does it have to be dependent on input? Even if I put one for loop after s equal to a plus b, if I put for I in range s, s plus equal to 1, let's say something like that. So it
What is
even
a for
without
loop?
putting the input, it will
Sorry, what is
be
a for loop?
dependent on...
No, what is a for loop for?
What is
Can you tell
sorry?
me the for loop? Can you tell me the for loop that you were saying?
For I in range s, after third line, if I introduce another line for I in range s, s plus equal to 1, let's say.
See, this s is not the input here, right?
Yeah, s is not input, s is variable.
No, s is not even variable, s is
S
constant because already the values are given.
S
A
is a
is equal
constant,
to
so the running time of this code is constant. See, what I am saying is, whenever there is dependency on the input, some function of n, where n is the size of the input, that is
So
where it
even if I
becomes...
put a for loop within this, it will still be constant. It will not be dependent on any external
Because
value.
S is a
That is why it
constant.
is... I agree to your point. But even in for that case itself, since it is a constant only, even if it is not 4, even if it comes out to be 24, it will still be a constant. That's what we are saying.
Even if it is 1 million, it is a constant time
It
algorithm.
is a constant, agreed.
Yeah.
So it's not dependent on input, henceforth it is not dependent on input.
That's what we say it as constant time algorithm.
Okay.
For any input, independent of the input size, the algorithm takes the same amount of time. You could just read and say some list, okay. That is okay, but you are not making use of the list. You are just having some constant time operations inside. Then it is a constant time code. Okay. So the next one is like this for loop, right? This for loop actually takes the n, which is the size of input. Yeah. So then it is an O of n. Is this clear?
Yes, ma'am.
So one thing you have to understand here is, see, this for loop is executing for n plus 1 is what I said, right? And this s is equal to s plus 1 will execute for n. Correct? Now we have n plus 1. We are adding the n, correct? Is this correct? We are just adding the n.
Why we are
That's
not
what.
multiplying?
So, as I said, this step actually takes only 1 unit of time, no? Is it correct? This step takes only 1 unit of time, right?
Yes, ma'am, it is okay.
If this internal step takes again n units of time, then you multiply, because for every value of I, you have to do this n times. Whatever is inside here.
If there is nesting, then only multiplication will be done, right?
Yeah. If there is some for loop and there is dependency of that for loop, both the for loops, both the for loops have dependency on input size. Okay, some factor of n. That is when. Yeah. Somebody is asking. Yeah.
Yes, ma'am. Can you move to the upper problem, like anyone talking about for I in range S? Yes, ma'am. Here, let's say there is a for loop is there for I in range S. S is equal to S plus 1. Let's say I am saying that, and after that print S. So, ma'am, here for every means, let's say S will be 5 here first. So for I in range 5, every time I am increasing the S value. So here means 5 is equal to, means it will be increasing every time when it is going.
No, what you're saying is for I in range S, correct?
S, yes.
S equal to S plus 1, is it?
Yes.
Can you do this? Will it not go to an infinite loop or
Yes,
something?
it will be going to infinite because every time s will be increasing
Yeah,
further.
it
So
will
that
never end. It
then the time
never end.
complexity is infinite. I mean,
So
see,
yes, I am asking that.
infinite is not a number. It's not a constant number. The value infinity is not a constant number, no? It's NaN is what you say, right? Not a number, right?
Yes, it means here the input is infinite. That's why,
No, it's
right?
not the input which is infinite. So input, there is no input to this algorithm basically. It is just
But it
initializing
will
some constants.
Ma'am, how it is infinite? Because S is the summation of 20 plus 10, so it will range will be 30 only.
No, inside the loop you are incrementing S, no? So you start off with say 0 to n minus 1. Okay, the first value is 0. Then you increment this, then you increment this, then you increment this, and when it reaches n minus 1, you still keep incrementing. Oh, okay, so then, but still the range is, this is what you're saying, right?
Yes,
But
ma'am.
but by the time you reach n minus 1, the S would have become n, no?
Yes. That is the thing now.
Then the next loop, S becomes n plus 1, right? Because
Yes,
you are
ma'am.
incrementing this. I think we'll have to hand run it, but the idea I get from what he was asking is, what if it goes to something like infinite loop? And see, those cases, it probably doesn't even make sense to do a complexity analysis. Okay, so let's come to the practical scenarios. Okay, so here you have a for loop and here you have a S plus. So what we were saying is like, yeah. So when you have nested loops, you multiply it because this will get executed n times. There is another for which will get executed n times, and this, for each value of this get executed n times. So you have to do the multiplication. Whereas this, whatever is there, this is a constant time operation. So this will get executed n times. This will get executed n times. So it's only n plus n, and that's why the complexity is some 2n plus 1 or something, where you hide the constants, remove the lower terms and everything, and you still get a O of n. Okay. Okay, so that is, so here again, as I said, like this is, so we already did something similar, no? F of n equal to, so 2n squared, maybe something, some constant factor, some difference might be there, but something like this. Then you remove all these things and this becomes O n squared. We did almost the same thing in the example that we discussed earlier, right? We had a for I in range and for j in range and s equal to s plus 1, no? So we had 2n squared plus 2n plus 3 or something because we had 2 or 3 other statements also here, but whatever. So here, this again becomes O of n squared because we are ignoring this coefficient and ignoring the lower terms also. Okay.
Ma'am, sorry to be repetitive, but I couldn't understand the n plus 1 steps in the for loop starting statement, line number 2.
No, okay. So then probably I
I
can give you some pointers where you can see how the Python is implementing the for loop. That will give you a better idea because I have explained multiple times. So possibly another attempt will also not work. I will give you a link. Just try it out. If you're able to understand after reading from it, please post it on Discourse. Even if you're not able to understand, please post it on Discourse. We'll try to
I'll do
respond
that.
there.
I'll do that. Thank you.
Okay. Yeah. It's not complicated at all. It's just how, it's internally done.
I'm trying to wrap my head around it, but since there is only n times it can execute, I was not able to get that n plus 1 factor only. I was not able to get. That's why 0 to n minus 1 it is going in for n times only, right? So
So,
that
okay,
will
let me
n
just ask you.
only.
Okay, how does the for loop get executed? How do you think the for loop? What is your intuition? How does it get executed?
So
There is
it
somewhere
initiates,
the counter is being tracked, right?
right? It
And
initiates I with
every time it
0.
reaches a certain value, it will check whether the maximum limit has reached. If it has not reached, it will go inside the loop. If it has
Oh,
reached, then it
okay.
exits.
Okay. So
So
that
the
last step is for that checking of whether it has
correct,
reached the
n,
final limit. All right.
when it reaches n, right?
Understood.
Yeah.
Makes sense.
There could be other ways to do it, but I have read it and I've seen that this is how Python has done it. There could be
Agreed.
other ways to do it. Okay.
Makes sense now. Thank you.
Okay. Okay, so here again you have 3 loops, each of which is dependent on n. So you have 3 for loops, right? So once you get this idea, and it kind of becomes very easy. The moment you see 3 for loops, each of which is dependent on n, then you have a O of n cube algorithm. That's it. Okay. The difficulty comes when you have a loop like this. So let me ask you, while I less than or equal to n. Okay, I'm sorry. Okay, I is equal to I into 2. Okay, so I is 1 first. Okay, I equal to I into 2. Can you tell me the complexity of this algorithm?
Ma'am, infinite.
Why?
Infinite.
Why?
Ma'am,
Root n.
because I is not incrementing.
No, I is not incrementing additionally, but multiplicative
It is
incremental
Nah,
is
you
there.
will
Na?
be 2. From 1 to it become 2.
N by
Then
2,
get
ma'am.
it become 4. It is incrementing, I guess.
Can you tell me? Somebody was saying n by 2, somebody was
Yeah,
saying...
ma'am. Is it
N
n by
by
2?
n.
No,
Ma'am,
it's
N
not
upon
n.
to the power.
Yeah, it's log n actually. So how do you get it to log n? Okay, I will just show you. Say for instance, n equal to, say I'll just take a multiple of 2 just to make it easy for you. So maybe 32. Okay. What happens when I equal to the first iteration? Okay. So let me put it as this is first iteration. Now I is less than n clearly because n equal to 32, right? I becomes 2 in the first iteration, correct? Okay, maybe just put it, sorry, yeah, first iteration 1, okay. In iteration 2, I becomes 4. Iteration 3, I becomes 8. Iteration 4, I becomes 16. Iteration 5, I becomes 32. And iteration 6, I becomes 64. And that is when it comes out of the while loop, right? Until this step, so I becomes 32, still it will go here and it will check and it sees that is less than or equal to 32, fair enough. It goes inside again, it again multiplies it by 2 and gets a 64, and then it comes and checks the while. At that point, it is less than or equal to, it's greater than 32, so it comes out of the while loop. So the number of iterations that this while loop will execute is 6 times. I'll
That
give you
last
an
step will
intuition.
not be counted when
Sorry?
it checks that
No,
last
it
step
will be
will not be
counted. It will be counted. No, this is one iteration. It's after that it goes and checks the while condition, right?
Oh, okay.
It is still counted.
So
That's fine.
that last step it will not get executed. That's the only thing.
No. See,
Because it is not.
this will get executed. This will get executed only when
It
it
got
becomes
executed in
64.
a step number 6, and it goes back to while loop, and then it checks that it is not less than 32 anymore. So henceforth it jumps out of that while loop.
Correct. When it jumps out, I is 64. Got it, no? Yeah. Now what is happening is, so I'll give you an intuition, not doing a really intense mathematical calculation here, but as you can see, the number of steps, right? It is actually the value. If it is 32, then for every doubling of the value, right? Every doubling of the value. So you have the first time it is 2 power 1, then you have 2 power 2, then you have 2 power 3, 2 power 4, 2 power 5, 2 power 6. So when it is 2 power 6 is when it is exiting, correct? So if the value of n is 2 power 5, then it will execute 5 times, correct? Sorry, 6 times.
6 times.
Correct, no?
Yes, ma'am.
So, which is nothing but if the value of, so if n equal to 2 power k, it will execute for k plus 1 times. Correct? So if n equal to 2, what is k? K equal to log n to the base 2. So you have log n to the base 2 plus 1. So it is O of log n to the base 2. Every time you are halving, right? Sorry, doubling, right? So you are reaching 32 faster and faster. So from 1 to 2, you had only one small step. From 2 to 4, you had 2 steps. From 4 to 8, you made a leap of 4 steps. From 8 to 16, you made a leap of 8 steps. So you are reaching 32 faster and faster. And that is reflecting in this logarithmic factor. So the number of iterations that you have to execute to reach that n value is, you have put it as, so if you have n equal to 2 power k, then you need k plus 1 iterations. So because n equal to, sorry, k plus 1, because n equal to 2 power k, k equal to log n to the base 2, which is log n to the base 2 plus 1 number of iterations are required for an input of size n. So, see, whenever you see a for loop, it is relatively easy because the internal increment. So, even for loop, you can actually increment additional factor only you can give, right? So, you can give something like range 2, comma, some additional factor, comma, the upper bound, right? You know that syntax, no? Range of I, comma, j, comma, k.
Yes, ma'am. Yes, ma'am.
Yeah, so that is also additional increment
I,
only, right?
j,
Multiplicative.
step also we have provided.
Yeah, but you cannot give a multiplicative increment there, right? I'm not sure if Python has such a for loop. But within the while loop, when you do this analysis, you have to be very careful about how the increment is happening. Inside the for loop, you don't have to worry too much if you see it's, you know, within a factor of, I mean, if it's making use of n, it will generally be n. The case of while loop, so it could also be that y greater than or equal to n, and I is starting with some 64, and then internally you're doing I equal to I divided by 2. Even that will be like a log n. So it can come in different forms. Got it, no? So it will be a log n because it keeps doubling at every step and you reach n at a much faster pace as you would when you are simply incrementing it by an additional factor. Additive factor.
Ma'am, is it always to the base 2? I mean, is there any case where we have a different base?
No, that's because we have put it as I equal to I into 2.
Yeah,
right?
if I have I into 3, so probably it will be to the base 3, right?
Yeah.
Okay, so
Yeah.
it's not a
So, but please understand that log n to the base 2 and log n to the base 3, right? This conversion can be done using a constant factor.
Yeah, yes, yes.
This is a constant factor conversion. So whatever is the base 2, we'll simply write it as log n. It doesn't matter whether it is log n to the base 2 or 3 or whatever. As long as it's a constant, it doesn't matter. But if it is some k, which is also part of the input, then you have to worry about it. Otherwise, if it's some constant, you don't have to worry because we can mathematically convert between the various bases of the log n.
Yeah. Okay. Thanks a lot. So in general, we say it is log n.
Correct.
Yeah. Thank you, ma'am.
Yeah. So that is just something that you have to be a little careful about these kind of analysis. Yeah, so that is one.
Ma'am,
Yeah.
just a little doubt. Maybe I just missed what you said in between. So, like, if we write instead of I is equals to I into 2, instead we write I is equals to I divided by 2. I mean, instead of multiplication. So still, we'll be getting
No,
log n.
then here you will have I is greater than or equal to n, and I you would have initialized with something like 32, and n you would have initialized with 1 or something like that. These changes will be there, but it will look different. But eventually, the number of comparisons or the number of steps will be the same, is what I'm saying. Because there you are. Yeah.
When it is dependent on the power of a constant or a multiplication, then it will definitely jump
Yeah, I mean,
on
I
to
don't
log
want to generalize. I don't want to generalize it because there could be so many,
so
corner
many
cases.
test cases I can
Yes,
understand,
corner
but right now
cases.
what you're discussing is essentially boiling down to that.
I'm just telling you, like, there are cases where simply you see a while loop and you say that, okay, and the while loop has this n factor, you say that, okay, this is a O of n. That you cannot say is what I mean. I mean, when you say something like while I less than or equal to n and there is a loop inside, there is this natural tendency for I equal to 1 to n, you say that's n, right? So for while also, you might be tempted to take it's an O of n, right? That might not always be correct is what I try to show you in this example. Got it, no? Okay.
Right.
So we have, okay, so this is simple. This is actually combining the n squared and n cube and everything. So again, you can see this is n squared, and this is n cube. Now we are adding n cube plus n squared plus n, right? So it is not nested for loop. It is actually one for loop is completely getting executed. Then you have another for loop which is getting executed. Then you have another for loop which is getting executed. So you will add the three complexities, which is n cube plus n squared plus n, which is again, you remove the lower terms and you get the complexity as n cube. So when you have these nested loops, it's a multiplication. When you have the consecutive loops, one loop starting after the other one is completed, then it is an additive. Maybe some of you can come up with, differences, examples which are different, but 99% this is how it is done.
Ma'am, where this complexity will be used?
Meaning the practical application
Where?
of time complexity?
Yeah, where it will be
Okay,
used?
let me just give you an example. Okay, let me just give you an example. Say, for instance, you want to find the shortest distance from, say, two cities, say from Delhi to Chennai.
Okay.
There are so many ways and you can go from Delhi to Chennai, right? You can go from Delhi to Bombay, Bombay to Chennai, Delhi to Kolkata, Kolkata to Chennai. There are so many ways in which you can do that.
Okay.
But there are graph theoretical modeling which is possible for these kind of problems, where each city you represent it as a vertex of a graph, and you can compute, you can come up with a solution which is doable in polynomial time. So the other case, right? So okay, so we have seen cases where it is O of log n, O of n, O of n squared, O of n cube. So I just want to tell you, like, this is the words which I used earlier. Okay, this is sublinear. Don't worry about this terminology, just telling you. This is linear. Okay, this is linear because this is O of n is called as a linear time algorithm, and it is directly proportional to, or directly, the upper bound is like some function of n, right? Not just, I mean, in terms of n only, not n, any other power of n. Then you call it as linear, because log n is strictly less than n, you call it as sublinear. Here you call it as polynomial time or p time. This is also polynomial time. So any power of n is polynomial, n power c. We call, see where c is a constant, we call it as polynomial time. There are other cases where it is 2 power n. This is also a function of n, but this is 2 power n, and this is like, you can figure out, like, for instance, say 2 power 10, 2 power, once you go beyond a certain value of n, say 2 power 10 is, I think, 1024 or something. Yeah. So you can just keep on increasing this value of then after a certain, say, 2 power 100 and all, it is very difficult to compute. So even for an input size of 100, you will take years to compute a solution if the algorithm has time complexity which is exponential, which is 2 power n. Okay, so suppose your algorithm, the one which I told you, right? You find the distances between all possible combinations of cities, and then you compute the shortest path between Delhi and Chennai, then it would possibly extend it to this exponential algorithm. And if you want to travel from Chennai to Delhi, you want to find the solution within a short time, right? You cannot wait for years to get the shortest path, right? But there are graph theoretic formulations and modeling of this problem wherein you can find the solution reasonable amount of time, just polynomial in the input size. Input size is the total number of cities, which is the nodes of the graph. Those things we'll come to it later. That's different. But yeah, O of 2 power n is basically useless. We cannot use it for large values of n. You can just put what happens if you put O of 2 power 100. You can see the value. Even for an input size of 100, it goes beyond manageable. So why the complexity analysis is required? I'm claiming, okay, I've come up with an algorithm. I've written the correctness proof for it. Fine. Is it usable? This is what I started off the session with, right? Is it even usable? Can I make use of it for some realistic purposes? That's where this complexity helps us. You have two algorithms, one which performs as O of 2 power n and another which performs it O of n squared. You will prefer the one which performs it O of n squared, right? Whatever be the hidden constants, you would still prefer it for O of n squared. This is the purpose of complexity analysis. So there is this big bridge or gap between this theoretical computer science people who come up with the mathematical proofs and notations and people who in fact practically implement these things. There are gaps, there are discussions, debates, everything that happen on these kind of analysis. Still, this branch of theory, the analysis and this has been still going strong because it helps to give us a very bird's eye view of what algorithm can be reasonably used. And then once you have something which is reasonable, you can try to optimize it by coming up with clever ideas and everything. So certain recurrence relations, for instance, I is giving the example of the Tower of Hanoi problem, right? So that has actually got a 2 power n solution. You cannot do the 2 power n for, if you have, say, disks, something like 15, 16 disks in it, it will take months and years possibly to get the solution. So if the algorithm is not even usable, what's the point of such an algorithm? So just for intellectual pursuit, if you're interested, there is this stream of, or there is this branch of algorithms which we refer to as approximation algorithms. That will come to it, maybe the NP hardness and all that there towards the end of the weeks, right? So there, what you say that, okay, I have a problem and I'm going to tell you that there is no algorithm which can do better than an exponential time algorithm for this problem. Nobody on earth can come up with an algorithm for this problem which is better than exponential. In such case, what do? You still have a problem to solve, right? But the best algorithm that anybody on this planet can come up with is something which is exponential. So do you mean that you drop the problem? No. What we do is, we either do it for a certain subset of problems or we do it something like approximate. You don't need the absolute solution, but you come for something like approximating the solution. You say that, okay, within a factor of some value, I'm okay to have some error. It's okay. I'm okay to accept it if you're able to give me a solution in a reasonable amount of time. So if you can have a polynomial time solution which is approximate, I'm still okay with that. This is totally for intellectual pursuit. There is nothing technical about it. So we'll just stop that discussion here. Probably we'll go to the other things. Okay, sorry. I just got a bit carried away with it. Okay, so yeah. Now we go to the linear search algorithm. Okay. So far it is okay. People who
Ma'am, can you show once again how did you find for the recursion?
Which one?
Recursion.
Oh, recursion, we did not address this one, right? Okay. Oh, sorry, we missed this one. Okay, we stopped at O of n cube and then we have to, okay, let me just clean up this. Okay. This one, right? This is what you wanted, no? For the factorial,
Yes,
finding the factorial,
yes,
right?
Yes, ma'am.
Yeah, okay. So what is a recurrence relation here? You want to find the factorial, for which we say that the time taken, which is a function of n, right? So this is just like our f of n only, okay? So we are just putting, just to denote the time, we say time t of n equal to, what are these dependent on? There is a constant time which is happening here, and there is a call which is going to the n minus 1 here, right? The same function is being called. So if this function has a complexity which is t of n, then this function will have a complexity which is t of n minus 1. Is this correct?
Yes, ma'am.
Plus, so this is one step and this is the next step, which is a constant time, right?
Once more, ma'am, how this came t of n minus 1?
See, you have factorial n. I'm saying that, okay, let me define t of n. Let t of n be the time taken or time number of steps or whatever. Okay. Time taken for factorial of n. Okay. What is the time taken for factorial of n minus 1?
Okay, t n minus,
T of n minus 1. This step takes t of n minus 1, right? And this is constant time. That is, so this factor plus this factor is there.
Okay. That's why addition is there, right?
Got it, no? Okay. Now what happens is you have, say, t of n plus t of, t of n equal to t of n minus 1 plus t of n minus 2 plus you have the O of 1 of this, right? Plus the O of 1 of this one, correct? Is it correct?
Yes, ma'am.
Correct, yeah. So now we are looking at the number of steps, right? So this means constant number of steps. So we can as well say that it is one step. Because it's like, say, if you have, say, 5 steps, you're just saying that all of them you're putting together and saying that this is one logical step. Correct, no? So it might be like 20 steps inside that, but what I'm saying is it's a constant time and it's one logical step. All these steps taken together is one logical step because there is no dependency on n, and I'm saying it's one logical step. There could be a constant factor hidden, there is no doubt about it. So for us, when it is t of n minus 2, here you have 2 ones. Now you have to go to t of n equal to 0, right? N equal to 0 is the base case here. Correct? Do you know? Okay, for any recursion, it is very important to write the base case. Otherwise, it will be you cannot stop the recursion. Okay, so this is the base case. So you have a value only when n becomes 0. Until then, you do not know what the function is going to return. Is this clear? So
Yes,
I'll
ma'am.
write, yeah, I'll write again. So maybe T of n equal to T of n minus 1 plus T of n minus 2 plus etc. plus T of 1 plus T of 0
Can you mute?
plus etc. Sorry, not plus etc. plus n into O of 1. Because see, when you had n minus 2, you had two ones here, right? So this is what n minus n. So you have n ones here, correct? When you had n minus 2 here, you had two constants here, right? So this is n minus n, no? This 0 is n minus n.
Yes, ma'am.
So you have a multiplicative factor of n here, which is n into 0.1. Correct?
Yes, ma'am. Can you show how you unwind this?
You want to see show once again?
No, how to unwind?
This is unwinding. What she
Okay, so
just did is
what you
unwinding.
mean? Okay, so this
So
we have to,
basically
sorry. Okay, I'll tell you what is the problem. I wrote it wrongly. This is T of n minus 1 plus O of 1, right? Now T of n minus 1 is what? T of n minus 2 plus O of 1. This is correct?
Yes, ma'am.
Correct. So when I'm putting n minus 2 here, I should not put n minus 1 because it is T of n minus 1 which I'm substituting with this T of n minus 2 plus 1. Got it now?
Yes.
Okay, I will write it again. I confused you. One second. So T of n equal to T of n minus 1 plus constant time, right? T of n minus 1 equal to T of n minus 2 plus constant time. So T of n equal to T of, I'm substituting T of n minus 1 with this. So I have T of n minus 2 plus O of 1 plus this O of 1, right? Which is O of 1. Now T of n equal to T of n minus 3 plus O of 1 plus O of 1 plus O of 1. Is this clear?
Okay, yes, ma'am.
So now it is clear, no? Now you have T of n equal to T of 0 plus n into O of 1. And T of 0 is already given in the base case here, which is return 1. What happens if n equal to 0 is what is given here? Return n, sorry, 1. In that case, you substitute this with T of 0 plus n, which is n plus 1, which is equal to. Okay.
Okay, ma'am. Yes, ma'am.
Yeah, recurrence
Thank you.
relations is not easy. This is a very straightforward recurrence relation, but generally some recurrence relations can be very tricky, and this you can do it only with practice. There are so many ways to solve the recurrence relations by substitution, and there are so many other ways to do that. So I don't even think like we need to know all those things, but the simple what we have seen here is a substitution, right? So Tn minus 1 we got as Tn minus 2 plus over 1 that we put in place of T of n minus 1. We kept on substituting until we reached the base case, and then the base case whatever value it written, we simply put it there and we got the value.
Okay, ma'am.
Certain recurrence relations may not be that straightforward. Okay, so it might be a little tricky, but yeah, we'll have to.
Like in merge sort.
Merge sort is also not that difficult, no? You have the T of n by 2 and then plus n factor, right?
Yeah, n by 2 plus n by 2.
Yeah,
Givo
but
of n by
finally
2
there is a plus n which is for the merge method, right? That is what
Yes.
gives the n log n, no?
Yes, ma'am.
Okay, we'll come to that. Okay. So I'll just finish the searching algorithms also. So, sorry. Okay. So this merge algorithm, merge sort, let us look at the merge sort first, and then we will try to understand this one. Okay, because right now if I tell you like why merge takes O of n, right, this one. Sorry, one second. Why? So this statement is the one that takes T of n by 2. This one takes T of n by 2, and this takes T of this O of n. So then you will not know why this is O of n unless you know the merge method, right? that we will see in the maybe in the next session or something. Right now I will just look at the two searching algorithms. Is it okay?
Okay, ma'am.
Yeah. Okay. So, but this recursion is clear, no? The factorial recursion is quite simple, right? It's clear, right?
Just one quick question on the factorial recursion.
Yeah,
If
yeah.
it was, if let's say one more nested loop was put in before the final recursion, and because of that it becomes dependent on n square. So will that lead to the final big O being n square?
So I'll have to think some time on that. Like we cannot give a straightforward in this thing depending on the where you're putting the for loop. Say for instance, you're putting the for loop for the if statement or for the return statement. Of course, you cannot put a for loop, right?
Right, of course.
So the for loop will be if it is instead of that constant. If you put a for loop which is dependent, then it will be n plus that value, right? Again, the n will that factor will get absorbed by the O of n.
So I understood that. I'm not trying to signify any particular step, but I'm just saying that if at all within that final recursion step, before the final recursion step,
So here, okay, what you
the
mean to say
factorial is
is like,
dependent on n square.
yeah, here you have a for loop, right? That's what you mean, right?
Yes,
Which
yes.
gets begins and ends before the return statement. That's what you mean, right?
Right.
So this will be O of 1 plus n plus again whatever you get from this whole thing, right?
Right.
So then this n will get absorbed in the O of n is what I'm saying, because it's only an additive n, right? The other one is also an n, this is also an n, so it's a 2n and this gets absorbed.
So, but connecting to that, if there are three separate components in a function, and let's say one of them is whatever, one of them is A, one of them is B, or whatever is the complexity, the worst one will dominate the overall algorithm. Right?
Correct.
So that's the max,
Yeah.
which Prof.
So in that case we saw here, this is what we saw, no? This complexity of combination of one.
Yeah.
So this is n, this is n squared, and this is n cube. And as I said, like these are happening consecutively. So you have n cube plus n squared plus n. So you remove this, and this is what happens.
Yeah.
Okay, this is fine. Okay. So let us go to the searching algorithms. Okay, so this is what the classic algorithms that I was talking about. So linear search is simple. Like this is some basic intuition that anybody will have, right? So if you want to search, say if you have a list of mark list of a student and you want to see if there is a student who has submitted the answer sheet or something, the natural thing that we do is we simply scan from the first paper, and whenever we find it, we say it's found. If we reach the end of the list and we don't find it, we say that it's not there, right? So here yeah, so here what is the input?
N.
What is n?
Length of L.
Length of L, right? And what is the other input?
Ma'am, the value we are looking for.
B, correct? Or we call it the key that we are looking for, right? So these two are the inputs, n and b. So this loop, this for loop is actually dependent on n, correct? No, but I'm just trying to, try to get it from you, like whatever we have explained so far, from that it is very easy to see this is an O of n. Does anyone have a confusion on that? Any confusion on this?
No, ma'am.
Okay.
No, ma'am.
So what is the best case? Why is it O of 1, best case?
Ma'am, it's because if we get that element V in the first iteration, then it will be big of 1.
Correct. Yeah. So that is why this is the best case. Average case, see, it is little difficult to explain also. So again, as I said, like whatever are the possible combinations, but you can do an average case analysis. So there are okay. So how do I do that? Okay. So first one, total number of comparisons in case. Okay, maybe I don't want to go to that, but this is just take it for granted. This is O of n. Okay, so this is not an average of best case and worst case. That is clearly not the case. Average case is dependent on the types of input that it can get and how much time that each of these input takes. So average case for now you can kind of ignore it in this case, the computation of which I'm not sure if it is even there in the lectures. So we'll just stick to the best case and worst case for now. Okay. Yeah, so the average case analysis is generally done in what is known as the randomized algorithms. Okay, so there are algorithms where we fix this. What do you say? We kind of toss a coin, and depending on that, we make a choice whether we move to the left or the right and all that. No? So based on that, whatever that the probability distribution from where we are taking it, we compute the expectation based on that, and then the average case is computed. In the case of, see, you can see in the case of quicksort, there is this randomized quicksort, which has a very detailed probabilistic analysis, and that's where this average cases become very important, because in the case of quicksort, you O of n squared the worst case, whereas the average case is very good, which is O of n log n. So those cases where the average case really makes sense, like most of the inputs will have a better, like it will not go to O of n squared, it will be really good, is that what we conclude from this kind of analysis. Okay, if it goes above your head, please leave it. Okay, it's fine.
Ma'am, what will be Fn here? Suppose in the naive search, how to calculate the Fn?
F of n, right?
Yeah, F of n.
So this will be for x in n. So we are doing the worst case, right? So this will be n plus 1. This comparison will be 1. This will be 1. So you can. So this is either of this, return true or false only will happen. So we can. This is 1. So this will happen again for n times. This will happen only once. Right, this comparison happens for n times, right? So it will be n plus 1 plus n plus 1, which is 2n plus 2.
Or return also it will be 1, return false.
Yeah, see, return true will happen just once, right? That statement will get executed just once. Unlike the incrementing s is s plus 1, which get executed n into n times, the return true will happen just once. No?
The first will be n minus 1 time, n times.
This will be n plus 1. The comparison whether v equal to x will happen for all values of x ranging from 0 to n minus 1, right?
Okay. And false, this return will statement will not be counted.
No, this is 1 is what I'm saying. This is 1 that I've added here.
Here return false is also be 1, na?
No, either return true or return false. One of these only will happen, right?
Okay. Either this or this is one counted one. And that one and define. Okay, fine.
Sorry, I'm asking this question again. I'm sorry.
Yeah.
When the length is n, why is it n plus 1? Because it's 0 to n minus 1, which should be n, right?
So I think I have explained this about 6 times now.
I'm so sorry.
Can we go back to the recording? Maybe we'll upload it in the YouTube and then please check it out.
Okay. Sorry.
Okay. Let's move on to the binary search. So this is a very interesting algorithm, which is probably not very intuitive for somebody who does this algorithms course for the first time. So, but see, the binary search is always projected as a very, a very high performing algorithm. But the catch is you need to do some pre-processing on the list. The binary search works only in the case when the list is sorted. But given the list is sorted, right, the binary search has a much better performance as compared to the linear search. Right, the binary search does not work on a non-sorted list. It has to be either sorted in ascending order or in descending order. One of these orders it has to be sorted. Only then the binary search will work. Okay. So what does the binary search do? It checks for an empty list. If it is an empty list, it returns false. Then it says that, okay, let us fix the mid element as the length of this thing divided by 2, removing the whatever as the function. I mean, if it is an odd number, you remove the fraction and you just settle for one of those. Okay. And this is, so if you find it as a middle element, then you return true. If it is less than the middle element, what happens? So you have a list here, say. Okay, 1, 2, 3, 4, 5, 6, 7, 8. This is the index. I have said 10, 16, 22, 45, 72, 99, 101, and 110. Okay. I'm looking for the number, say 99. Okay. What am I doing? I'm taking the length of L by 2. What is length of this function? What does it return? The mid as this one, right? Is it correct?
Yes, ma'am.
So, I mean, length of L is 8, right? So 8 by 2 is 4 you have here. And so now mid is this one. So we are checking what is the value B equal to 99 for this, right? So if I'm checking if B equal to L of mid, which is L of 4. So mid equal to 4 here, right? I'm checking if L of 4 is the same as 99. If it is true, it returns true. It is not. Now what I'm saying, B is less than L of mid. What does it mean? If B is less than L of mid, is B less than, so 99 less than 45? No, it is not true. So you go to the else part where there is a recursive call on this binary search with a new list which is defined as the one starting from mid plus 1, which is 5 to the end of the list, which is 8. Now this is the new list L, right? Got it? No?
Yeah. Yeah, got
Now
it.
again the recursion comes here. This is the mid value, right? Now I see that L of mid is equal to V, so it returns true. Now the interesting thing that you have to see here is the slicing technique. That is what is written here. Due to use of slicing, this implementation takes O of n time. The Python internally, this slicing takes O of n time. So the regular implementation, so sir has given it just to discuss the concept, but if you want to do a finer analysis on how much time it takes, you have to stick to this algorithm. This is this. Or there is this binary recursive thing without the slicing where instead of just the list and the key, we also pass the starting and ending of the list. So here we are giving starting and mid minus 1, which means, so this I'll explain again possibly in the next session also. Maybe I'm just rushing through it, but yeah. So I have a mid value here, right? Now, if my value that V, this a value that I'm searching for is less than L of mid, then my new list, the list which I'm passing here, the list of the indexes which I have to search for is from the S. So S is the starting, say 0 to length of L. Okay, this is this list which I'm searching for. Now the end of the range that I have to look for is mid minus 1, which is here. So S is still this, S is still 0. Now this is the end of the list, which is mid minus 1. So my new list is this one. That is what it is showing. So here there is no slicing. So it takes only log n. So why? As we have seen in the case of I is becoming I into 2, there I told you if what happens if I becomes I divided by 2, right? Here also the same thing is happening. The n value, the length of the L, whatever the I is the intermediate, the length of the list that we are considering, right? In every loop. I think there is a bit of a noise. Can someone mute? Like, I don't know who's. Yeah, thank you.
Ma'am, if I may interrupt, why is there no slicing? Because still we do E plus S divided by 2, right?
No, that's a constant time operation. But Python, when it does internal slicing, it will actually do an O of n operation. Just like I told you, the for loop, it takes n plus 1 operations, right?
Yeah.
Just like that, the slicing takes O of n for Python.
Any slicing, is it, ma'am?
No. Python internally, how Python implements slicing. So in this code, with respect to Python, which uses slicing, which is specifically given sir's lectures, right? That is for your understanding. You can just assume that the slicing is a constant time. But if you want to do a finer analysis, you have to do this one where the mid is computed using this constant time operation.
Okay.
The slicing is not a constant time operation, whereas this one, this division, this you're finding the middle one, right? That is actually a constant time operation.
Okay, but ma'am, the previous code that you showed, even there, if I go back to sir's lecture, he has used the n by 2 thing and then given it as log n. This one,
Yeah, that's what we wanted to clarify. In the lecture, sir has given it, assuming that you can just take it for granted that the slicing does not take it. But we are telling you specifically just so that you know it. When you write actual code and you see that instead of log n, it's giving an n per O of n performance, right? You should know why it is doing that. So just for teaching the concept, sir has used it just to avoid this so many indices, so many tuples like in the input. No, now it is simple here. L comma V and what you understand it. So if you just accept it that the slicing takes only constant time, it is fine. But internally, if you do a deeper analysis, you will see that the slicing takes O of n. So if you want to implement the binary search in O of log n, you have to use this algorithm. If you want to use recursive version, you have to use this algorithm.
Okay. So before I define this function, I basically take the starting and ending point of, and then give it as a part of the function in this case, right?
Correct, correct. The arguments, number of arguments in that function is changing.
Okay.
Instead of just the list, I'm also telling you what is the range that I have to look at.
Fine, fine. Yeah.
Okay, and I redefine the range every time the binary search function is called. I redefine the range.
Yeah. Fine, ma'am. Thanks.
Ma'am.
Yeah.
Here, that log n is happening due to I is every time I is dividing by I by 2, right?
That's what I was coming to. So here
means
we have
it
seen.
Will be actually the base will be log half n. Means actually it will be like that. Log half n and
no, best will be O of 1 only if you find it here, no?
No, not I am talking about the best. I am talking about the worst case. But I am saying that in previous we have like in while I is equal to I into 2. In that problem we are getting log 2 of n. So here we are dividing I into I by 2. So that will be I log base of half into n. Means a log.
No. They're also no. That's what you are confusing. See, it is not whether you are multiplying there by 2 or dividing there by 2, which results in the base. Why 2 came is there because the number of comparisons is reduced by half. Not the number of comparisons, the number of steps inside the while loop is reduced by half every time it goes, right? It goes from 1 to 2, 2 to 4. So the number of steps, because of that, it is not because, it is not because you're multiplying by 2 that the base is 2 here.
So
you
here,
have to look at,
here, ma'am, it is means it is every time it is dividing, na? Divided by 2.
Yeah,
so that's why. Okay, got it.
Yeah, so here you can use a recurrence relation. Actually, it is. You can do a similar kind of analysis, but here it will be n by 2 plus. It will be a constant time, right? There is no n factor here. This is constant. This is constant. Constant. So this will be 4. So this is clear for everyone, right? Let me see whether the recurrence is correct. So I'm guessing this recurrence is correct, okay? Because we are only going to one side of the array. The other side we are totally ignoring. We are never going to go that part, right? So it's only
we are halving that array.
We are halving. Yeah. So here you will have T of n. Then you will have T of n by 4 plus O of n plus O of 1 plus O of 1, right? Something like this. So you have to do the same way. Like when the base case here, you have to see, right? So when this, what is n? It is the size of the list, right? Length of L. So if E minus S is less than or equal to 0, return B equal to.
That means that n will be 1, na? E minus S equal to less than equal to 0.
So once E minus S, when does E minus S becomes greater?
The list contain
less than or
one
equal to
element.
0. Yeah. Sorry?
Ma'am, it is equal to 0 when the there is one element is present.
One element, correct. So then this n by 4, you have to do it till T of 1, right?
T of 1, yes.
You will have to find out how many times you have to add this O of 1. This number is what will give you the. See, you do it 2, you get 1. You put it 4, you get 2. You put it as. Let me do it. T of n equal to T of n by 8 plus O of 1 plus O of 1 plus O of 1. Correct, no? So this is T of n power by 2 power 3
to the power k
equal
it will
to 3.
give k times O times O, na?
Sorry?
Ma'am, if it will be T of n by 2 to the power k, then it will give k times O.
Correct. That is what I'm showing. Say, for people, I'm not skipping one step because this 8 is nothing but 2 power 3. And whatever is this value is the number of ones we have here. Got it, no? And we stop when this n by, so for n by 2 power k plus k, right? So we stop when this becomes 1. This is the base case for us, right? And this becomes 1 is when we stop. So that is equal to T of 1 plus K, where n equal to 2 power K. The same computation that we did, we get log n to the base 2. So this T of n now becomes log n plus 1, sorry, log n plus 1, which is nothing but O of okay.
Log n plus 1, why 1?
Sorry?
Log n
No,
plus
T
1.
of 1 will be 1, no? What is it returning?
Okay.
What is T of 1 returning?
Yes, yes. Return B is equal to L of S.
Yeah.
Yes, that's why it will be 1. Okay.
So you should not forget the base case. It could be some important value. Okay, so you cannot always forget the base case. Okay. So this we get. So is it okay for everyone how we expanded it? N by 2 plus 1. Now n by 2 you substitute by n by 4 plus 1. N by 4 you substitute by n by 8 plus 1, and it go on, and then you get a pattern here, right? So if it is 2 power 3, then you have 3 constants here, which is 3. So if it is n 2 power k, you have k constants here. So then the base case, which is t of 1, which means that n by 2 power k equal to 1. That is what we have written here, n by 2 power k equal to 1, which is nothing but n equal to 2 power k, and k equal to log n to the base 2.
By getting the pattern, we have to find out the value of n.
Correct.
General value of n.
Not value of n, function of n. Yeah.
Function of n. Function. Okay.
Okay. Yeah.
Okay. Okay. Thank you, ma'am.
Yeah, sure. So I think I'll wind up for today.
Yeah.
We'll continue the discussion in possibly next session, or maybe we'll have another session to discuss the sorting.
Yeah. This sorting will be discussed once more, ma'am. Yeah.
Yeah. So you can just sorting. I have not started at all. So I will actually do the sorting. Maybe in another. Maybe we'll have some extra session or something. I don't know. I'll check with others and let you know. The insertion, selection sort, insertion sort, and other things, right? So we have to do that. So
one last question, ma'am.
Yeah.
So what about this? It may be silly, but whether the algorithm is stable or not. Stability of algorithm.
Unstable sorting is what you mean. Unstable kind of.
Yes.
See, okay, I think I am not sure. I want to just explain. So, unstable sorting is something what I'm going to tell you. So, suppose you have an input, say 1, 2, 3, 4, 5, or maybe 3, 2, 4, 5, 1 or something. Okay. Then you know that the order, final order is going to be 1, 2, 3, 4, 5, right?
Okay.
What if your list has 1, 4, 3, 4, 5? Okay, your list has duplicates and you have 2 4s. Are you going to distinguish between these 2 4s? This has a specific name. I'm assuming this is what the unstable sorting, unstable this thing means. I will check and get back to you again. But I remember, like, are you going to? So you have 1, 4, 3, 4, and 5. Now the final sorted list will be 1, 3, 4, 4, 5. So whether the same 4 is appearing, like the 4 that the 4s are appearing the same order in which they appeared in the input. Got it? No? I think that is what the unstable thing is, but I have to check. I'm not sure.
There was a question in graded. That's why I.
Oh, okay. Maybe I should have been more careful. Atul, does it matter? Like, do we have to remove the question from graded?
Yeah, so we can explain what is the stable thing. So
that is okay, right? Yeah, I hope I didn't give away anything.
Yeah, you are correct.
Yeah.
So the similar value should remain on the same position as the input.
Yeah, right.
For the stable.
Yeah.
Thank you. Thank you.
Okay, sure. So I'm stopping the recording and we'll join maybe next session. Okay.
Thank you, ma'am.
Yeah, thank you.
Thank you, ma'am. Good night.